Hello, everybody. How are all of you tonight? And wow, you're all chatting. and, and that's very funny, Siuni. We are actually building an exact service for streaming, which is a whole other series about CSG flicks. And but that's not what we're talking about tonight, because we have a special guest for this session. This is the C as an additional language session with the Enceladsaurus. Did I say it right?
Yeah, you got it.
Okay, I totally said it right. All right, so Enceladsaurus approves of how I'm saying it. So she's on via Discord. She's a astrophysicist by day, C coder by night, and she's accepted the challenge to try to learn C. You mostly work in Python, right?
Yes, yep, pretty much exclusively in Python.
Okay. And she just decided that Python, being such a beautiful language that it is, and I know everybody in chat agrees with me because Python, she just said, well, Python's doing all this wonderful stuff for me, so I want to get rid of all of it. I want to deal with all of those things. I know Siuni really loves Python, but she's by the way a bit of a Python non-fan, you could say. And hello, Miss Sagittarius and Strophium. Stay safe with constructors. We're not doing C++ Strophium. We're just doing bare metal C. So I don't know. We might go on to that later on, but for now we're just getting started with the basics. I don't want to get into all the class stuff and the oops stuff. We're gonna stay like procedure. We're gonna code like it's 1970. Actually, we're gonna take a bunch of the newer features from C, and by newer in C I mean C 1999. So we're going to program like it's 1999 in the C99. So the back end of this thing is hooked up to the C99 standard, and I'm pointing at the thing because I'm pointing at my screen, and you can't see that. So I'm gonna get to that. But we are literally, as Strophium says, we are literally programming the matrix. So I don't even see it anymore. I just see. All right, I'm not gonna quote it. We've all seen it. We've all seen it. Now we need some more 90s music. We totally need, you know what? No. Okay, all right. There's a
now you gotta have your background be like the green numbers or whatever from the Matrix. Instead of the bricks, it should just be like the Matrix whenever we're doing C.
Let's do that. Okay, I will. Let me make a note of that. Matrix roll for background. Didn't they do some analysis on it? It turned out it was like a sushi recipe or something that they were like showing in. Because there was a bunch of like Japanese and like random stuff. You have blue hair right now. Wow.
I got bored when I was recovering from COVID, and there was this like conditioner or something you could put in your hair instead of actual hair dye. And I was bored, and I was sick, and I was like, I really need something
that's
to
like
not.
Serious anime power up, I think just happened.
Yeah, I had purple and green hair in grad school. And then volunteering for the fire department, you have to have natural hair, but the fire department is prohibiting volunteers right now because of COVID. So I was like, okay, I've got this tiny window, thank you, virus, where I can have like cool hair for a while.
Very sorry, I didn't mean to cough in your ear, but it caught me off guard there. So that's great. Yeah, it totally did happen. So I need to get out of this monologue. I just want to show everybody here we've got something new, something old that's something new, which is we're going to go to the learn screen.
Something blue.
Yeah, something blue. And if we get that right, we've got this. This is the newest version, like as of minutes ago. You can check the GitHub repository. I think let's see what GitHub says about it. Well, this is the multi-user pad that we're using for tonight's session. And okay, it's now calling it an hour ago, but I think they have a bit of a rounding bit of fun. Oh no, okay, all right, pushed it at 6:20. I'll give them an hour. Yeah, all right. So I just deployed it, so it doesn't match exactly on the timestamp here. But this thing is like hot off the press. So this is our new learning tool, and for those of you who've been here before. Cool. This is mostly the same. A lot changed really on the back end, but we have our whiteboard up here, and we're set to C mode because Jesse doesn't fool around with these other languages. I mean, we have Python, we have JavaScript, but we don't have time for that stuff right now. Like we're in C mode. So lock and load. We've got
JavaScript.
Yeah, ew. I'm totally with you on that. But
seriously, my manager at work, well, my career manager, likes to tease me because my initials are JS, and so whenever he was trying to get under my skin, he would just be like, "All right, JavaScript," and I'm like,
"Oh my god."
That one would make me cranky.
I will try really hard never to make that joke. That just sounds awful. But okay. Especially considering like one of JavaScript's main creators, Brendan Eich, just is totally washed his hands of it.
I don't blame him. I'm sorry if there are any JavaScript programmers, aficionados in chat. I mean, I apologize for your existence, but
we all have to slum it in the browser. I mean, at some point, we're writing JavaScript.
Strophium. Oh my gosh! If I ever have a baby boy, he can be Jason.
Wow, I saw a Twitter handle I thought was kind of clever about that the other day. Sorry, this is not a just chatting session, but we're totally just chatting. But I saw one just like yesterday, and it was Jason Born.
Oh God. Oh, I mean, that's an excellent username. I'm kind of I want to go back in time and steal it, but
I know it's so good. I totally loved it, but I don't know if he's any good. I followed him. I was like,
just for the username.
You got me on the username. I might regret this later, but anyway, I know nothing about Jason Bourne, but I think it's great. Okay, so where we were last time, we had just had our first intro. It was several weeks ago. Jesse's been having fun.
Sorry.
Yeah, but she's back in action. So we're going to do a little bit of review. We were just doing a little bit of warm up right before the show just to make sure the tools work. And Jesse got a program running here. And we have a brand new feature here, the clear output feature, which some of you might have seen us live code. Was, it actually synchronizes the call. So there's a bunch of cleanups. And anyway, I by no means is multiuserpad ready for general use, but we're getting there. It's open sourced. It's got synchronized output clearing. We're just like, we're totally off on features at this point. We're gone crazy. Yes. Curse you, COVID. She was out for a little bit, and I didn't want to push her too hard because I feel like, even though she was offering to go like last week and, a little bit before that, I was like, you don't really want to be doing C when you're not feeling well, because C is going to make you feel unwell. So you want to be at your best before you go into C. So.
Oh Lord.
So I think my ulterior motive here is to teach you that as much as you're going to know about C, you're probably going to be happier in Python, but that's just my bias.
Probably. I just want to be a better programmer, and
it is great for that. That's a great reason. Sorry, I got really excited.
I know. I mean, that's the enthusiasm, right? Like I love programming, but apart from a smattering of MATLAB that I learned in high school because I had to, I've always just written Python, and I'm not very good at it. I'm self-taught. Like, I love it though. That's the thing. And I want to get better. And from what I've been talking to software developers, I've been asking, how do I get better? And they're like, well, do you want the easy way or the nasty way? And I'm like, well, obviously the nasty way. And they're like, learn C. And I'm like, okay, well, here we
do you want to get better? Do you really want to get better? If you really want to get better, this is it. Like that is right there. That is the greatest reason to learn C. A lot
feels
of
like going to the gym, when you haven't gone to the gym in years and you're like, this is going to hurt. This is going to be worse. Horrible.
This is worse.
But I'm going to thank myself.
This is like climb the Great Wall and just do the whole thing, and you haven't been practicing.
Wow. Okay. Well, you know what? I love to set goals that seem impossible for myself.
No, it's not impossible. But you'll hurt by the time. It's mostly flat-ish until it isn't. And you'll be in pain at the end, but you will have accomplished something like pretty serious. So.
Oh jeez.
Okay, not that I recommend going to China right now. So anyway, my bad, bringing that up. So yep, very sorry.
I don't know. The U.S. is pretty bad, actually. Don't come here, please.
Yeah, that's just a bad analogy. Okay, but anyway, moving on. So this is our tool. We have the latest version deployed. This exactly matches what's in the repo, and I don't recommend you run this at home. So just wait a little bit. And just for fun, I added, just because I was getting annoyed at doing the deployment, so I added a little scripts directory, and there's this rough install, and I tried to name it rough install because it should not say install. I feel like that sets the wrong expectation. But rough install has one of the best lines of code that I've written, which is right here. This is the I am crazy line.
Yes.
That is it. Like that, if you really want to do this, like this program by default will reject your attempt to install it, and it will caution you. Say, if you really want to do this, then set I am crazy to yes. So the only people who should be installing this by script have to declare that they're crazy. So that's as strong a warning as I can give you. So you might want to just watch the coding sessions until this thing matures a little bit more. But anyway, that is coming soon. And it's mostly written in Python. So if you're a Python dev, then, maybe we'll get around to that if you're around for some of the streams. I mostly work on that Wednesday nights. But right now, as Suni pointed out, I'm currently building a streaming service from scratch. That's CSGLearn. So pretty much all of the sessions, aside from these learning sessions with on Mondays with Jesse and Tien, are the only exception. Everything else is just like CSGLearn. So that's fun. You can check that out later. But when we get back to normal, we'll go back to improving this tool on stream. Okay, so that's just enough to get started. You're clever though, as fellow deep end diver. This is the best way to get it. Oh, and thank you for the follow, Strophium. I appreciate it. This is the best way.
Strophium is super cool. Just as a small introduction from my.
If I remember on your stream, Strophium's the dude who built that
yes
planet simulation in.
Yes.
Okay.
Like all of the cool video game development and often astronomy themed. Super cool.
Okay. Well, thank you, Strophium. I appreciate it. Thanks for dropping by. And I agree. This is a good place to deep dive. So, all right. Well, that's enough talk. Let's get to some. What can you do with C? You gain some serious power.
Oh yeah.
And this is exactly what we're
going
to do.
Yes. Is that the glove you were just telling me?
That is the glove that I was telling you. This is it. This is the power glove. We are that sensor that you saw at the beginning of the show. That is the BNO 055. It is a 9 degree of freedom position sensor. It is going to be going into that power glove. So we are going to hack time, but we're going to get to that a little bit later. Okay, so no, we're well beyond the meme, Strophium. Don't worry.
I can make your power glove print every letter from A to Z.
I really like what you're saying, because
you never know.
That's a really good way to warm up. We should really do that.
Oh, you want me to write it again? No.
So there it goes.
Shoot. Oh, that's cruel.
Fafi, you are absolutely right. I only get the power from the power glove when I'm typing with it on. I'm just gonna have to go a little bit less power because the Enceladorosaurus is driving, and she's already driving. So yeah, it's been too much Python in the intervening few weeks. You're just writing pseudocode.
Don't you even start with me, all right? You know what?
That's totally how we roll.
Pseudocode saves lives,
no,
all right?
I that's why I like to program in pseudocode, which is Python programming. So
let's see. So while I is less than equal to... Okay, and because of... Oh, lordy. That's not the right thing. And then I want it to end at the end of the code. Oopsies. I lost track of my brackets. There's too many brackets.
Oh, we could do Lisp if you really want to lose track of your brackets.
I looked at Google images of Lisp when I was like 15, and I was like, oh, someday I'll like. So really tiny fast story time. Okay. So when I was like 8, my mom made the mistake. I love my mom dearly. She made the mistake of getting me a college lecture series on astrophysics. And so if you go back to little baby Jess's pink sparkly diary from the age of 8, there's random doodles of like Sailor Moon and stuff. And then there's like complex cosmological equations that I copied down from this lecture series. Awesome. I didn't understand, but I like told myself as I was writing them down, someday you're going to understand this. I'm going to know this. So then fast forward a couple, a decade, and like 16, 17-year-old Jess is learning MATLAB and falling in love with programming, but being told she's terrible at it. So, I'm still working through that. And
we're going to fix that.
I learned that Lisp exists. I looked at what the code looked like, and I had that moment of like, someday you will understand. I went back probably in the last few months, and I was like, yeah, probably never gonna understand what that means. Nope. Probably not.
I think it's amazing that we're talking about Lisp, because I had absolutely no intention of talking about Lisp, but this whiteboard up here is actually drawn with a program called MyPaint. And MyPaint, which I'm showing here on the top left menu bar, you can't really see it, but it says MyPaint up there in really small text. And MyPaint is actually a derivative of GIMP. So I don't know if you've seen look at you getting that program right. Nicely done. GIMP.
Yeah, I remember things.
Which is the GNU image manipulation program. And,
have you seen the fork of that?
Well, this is a fork of it.
Well, so there's a fork of it to like name it something slightly less sort of offensive.
Yeah.
And they've actually fleshed it out quite fully, and it was really nice to see
that cool. No, I haven't seen it,
but
I
be
will
like,
totally
yeah, I'll send you a link.
Yeah,
it's pretty cool.
I really like the pillow divide. I don't know if you've seen that in Python, but you know, modern pill is like when you do import pill, like the Python imaging library, it actually is pillow. because of reasons, but anyway, yeah, forks and projects are fun. But the reason I bring up the fact that this comes from the GIMP tree is that actually runs the language that is used for a lot of the macroing and filtering is Lisp.
Okay.
It totally is Lisp. So there's going to be Lisp powering this stream tonight. So it's not just a theoretical language. We are literally going to be doing a little bit of Lisp, but just we're not going to do it in the editor, at least.
Preferably, at least let's get through. And I would love to have you do a Lisp series next. But
oh god, I haven't done Lisp in years. I ran away.
As a linguist, so that was actually my original background. Any kind of communication system, whether it's a coding language or just some kind of ancient long dead language with really cool orthography, I just geek out when it looks really incomprehensible, because I had that sort of someday you will understand it feeling when I started to learn Arabic, where the script just seemed impenetrable to me, and I was like, someday you're gonna understand it. And when I was living in North Africa and reading the newspapers, it hit me. I was like, this is that someday. And so Lisp still kind of has that appeal to me of like, someday maybe I'll look at that and not be terrified or be completely lost, because it's really cool looking, but also incomprehensible.
Awesome about Arabic, but trust me, I ran away from Lisp and I am not looking back. I look at it and it's incomprehensible, and I look at it now and I go, I'm glad that I could decode that and don't want to.
Well, fair enough.
One of the biggest takeaways from learning Lisp is it will make you a badass with bad word.
You were the first one. It
will make you an awesome person at recursion, and you will recurse like none other after learning Lisp. Like, it will cause you to master it, but it is not fun. So anyway, I don't want to, if there's Lisp programmers here, you're probably Emacs people, so I'm on to you.
But we still love you. Thank you for being here.
We still love you. Thank you for dropping by. Okay, so let's get down to serious work. All right. So the first major change we realized when we started with C was this declare line on line 5, because before in Python we didn't really have to worry too much about memory. Memory is really handled as much as possible by Python, but in C we have to be quite explicit. So we have to declare a type before we go doing anything, and then we use whatever the variable name is. So oh no.
Oh, it's okay. I don't mean to distract him, sassing.
No, it's great.
But I can
actually.
learn.
That's a great. But okay, so we have to declare types. We have to be careful about them. And the types that we covered last time were not. There's not too much in C that we have to worry about. There's basically just int, char, and float that we're going to worry about. There's a few. There's modified versions of all these types. So I can have unsigned char if I want.
Wait, what?
We're going to get into that later. And I don't think I can have an unsigned float. That wouldn't really make much sense.
Signed and unsigned makes sense for integer.
I could have an unsigned.
What is an unsigned character?
Yeah, because characters can be negative. Wait,
what? How? How?
Okay, we're not going to worry about that. But it is, it's kind of a remnant of a much older spec, partially because if you set the high bit in most of these types are using 2's complement, which we're not. We'll go into 2's complementing later. I'm pretty sure with a Python background, you've probably never seen a 2's complement.
I have no idea what you're talking about. I'm sorry.
That's good. That's good.
Okay.
I would expect. I would be really surprised. I'd be like, she's totally hustling me. She knows C like a champ. If you knew what that was, so
okay,
that's totally fine. So I'm throwing the glove on, as you can see, and not the power glove. I'm going to the. I guess we'll call this the less powerful glove, but this is what we need to get to the whiteboard. And yes, this is the 2's complement, or as being said in the chat, this is the 2's complement. I'm going to switch over, since I'm going to be whiteboarding a little bit, I'm going to switch over to the whiteboard scene. So
make this bigger, theater mode, so I can see.
Yeah, we're gonna use the integrated view pretty soon, but I think it's a little bit easier to see for everybody at home if they're doing that. I'm gonna assume optimistically you're at home and you're not at work. You should be doing your own
Tyler.
Programming.
No, why are you here? No, I mean that's mean. Hi, Tyler.
Oh,
welcome to. No, so Tyler is my former coworker.
Okay.
He's an amazing machine learning engineer. Recently has moved on to another company, and I'm really missing being able to Slack chat him during my boring meetings.
Oh, you gotta build another Slack.
Right? But he's the person I reach out to with the kind of panicky situations I was talking before stream about. So when I'm completely stuck and somebody's expecting me to make it work and I have no idea how to make it work, I go to Tyler. So he is my encyclopedia of all the things. So
I'm drawing a wizard's hat.
Yes, that's Tyler.
If I could, this is not a great wizard hat, but I guess
a wizard hat of machine learning somehow.
We gotta like lean in, I'm just okay. So we can draw and do all the wizardly. I guess glyphs have to be in Elven. Yeah, all right. So let's get out.
Oh, I got you. Are we going Tolkien?
Okay.
I got you.
Hey, it's part of Unicode, so it's totally allowed. All right.
It's basically Elder Futhark. We're fine. Anyway,
yeah, we're totally fine here. Okay, so we did a little bit with types. I want to talk. Let's just review really quickly, kind of like what we went over. So we have int, which is short for integer. That's our basic integer type. We have char, which is short for character, which is our single character type. This is like a single convenient sized number. They eventually managed to specify it properly, and we have float, which is our basic, floating point decimal type, decimal in our normal sense of decimal, as in like 3.14 kind of sense. So that's, although I'm actually strongly against this. I'm a tau person, so let's be tau people about that. Okay. So Jess, yes, I'm sorry, Tyler. We're gonna try to give her the wizard hat in stages.
Oh no, oh, it'll take some time.
Okay. So those are our basic
I need
types.
a beard.
That's beard is like a state of mind. Okay. So all of these types, they have different sizes. So let me just quickly talk about this. This is 8 bits. This is typically, we're using C99, and in C99 this is 32 bits. And this,
I have a really stupid question. I'm sorry.
No, go ahead.
You keep saying C99. Is that like a standard for C that happened in 1999?
C
or
in 1999.
Okay, just making sure that I'm following you.
No, you're totally fine. As opposed to like C87. Which,
oh wow. Before I was born.
Yeah,
okay.
Yeah, like that kind of thing. Or actually we could just have C, which could go all the way back to like K and R type of C, which is like we're not writing there. So we're focused on C99 syntax, which is
C99 modern?
That's considered modern in the C world.
Oh boy. Okay.
That's if you want to get to like stuff that's moving really fast, then C releases way more. They have new specifications way more often. C kind of by its nature is like more regulated by the UN these days. So it's like, it just doesn't, it moves very slowly, like to get something in the standard. And C by its nature, they don't want much to be in there because changing the language, like most of C is intended to be a very stripped down language by nature. Like it's supposed to be just kind of a bare, like this is your machine and this is your machine on C.
You want to download a C.
So that's like yes. Really low level, even though like that's okay. So so that C99 is pretty much what we're going to be covering. There is a C11 as pointed out in chat. We're not going to use any newfangled stuff like C11. So that's none of that. Okay. So great. Then these types, actually, they do change from standard to standard. So yeah, this is part of why they don't really like to change it, because when they do change it, like a lot of code tends to break, and that costs a lot of money to fix. So I don't, that Strophium's comment, I don't, C++, I actually am not really a fan of C++, but we'll.
Oh, I feel like that's probably, whenever somebody, even though I don't know C and I don't know, but whenever somebody says, oh, like they say a disparaging comment about a coding language that's not JavaScript, I feel like those are probably fighting words. Like there's got to be, right? Because I feel like every time I've heard so many positive things about C++, about its versatility and kind of all of its various applications.
If you've heard a lot of things about positivity from C++, I need to ask who you're talking to.
Well, we can have that conversation, but I definitely had the conversation. Okay, if Python is not making me the best programmer that ever could be, what should I learn? And I mentioned that I wanted to learn C, and some people said, no, actually learn C++. And then there was a whole nother group of people that said, no, learn C#. And I'm like, there's too many C's.
Yeah.
I don't know what's going on.
We should really get into that. That's a whole stream right there. But all right, we're learning C, so let's just learn C. Okay. So we have these basic types. So bits, we're dealing in bits. Bit, not sure if you're aware of this, comes from binary digit. It's just a contraction. You know, we take the it and the b. Actually, we might take the I and just factor it out, and we get a bit. All right, so bit is a 1 or a 0, so we're just dealing with regular binary. So how much is 32 bits? How much is 8 bits? Let's start with the basic type of character. So a character is 8 bits wide. So if I've got 8 bits, what's the maximum number I could store? Now, I'm going to avoid the trick question here for a moment, but it does get to what you asked earlier. So this could be a 1 or a 0. There's 8 of these, right?
Okay. So hold on. I got this. Okay.
So
we
the
would want
largest
to...
number I could store, possibly, is this. Every one of these positions is a 1.
What number is that?
Yeah, what number is that? Well, that's what it is.
256?
No, it's 1111. It's and that's something that's going to come up a lot in C. Like, regardless what your representation is of the number, it's still the same number. It doesn't matter if you're using a base 2 system like this binary stuff, or if you're using a base 10 system, or a base 16 system, which we typically use to represent this, because base 16 is nice because it's 4 of these. So that's the reason we tend to like hex. So this maximum number, oops, kind of going a little bit too far down here, but this maximum number can be shown as FF. So FF, or all these, this is 8 ones.
Mm-hmm.
You got a guess, or should we?
128.
So 128 is actually 7 bits. It's actually, 127. This is a little bit of a trick. So if I one way to calculate this is I could imagine that if I add 1 to this, I've got 1, 1,
Oh,
1.
I was right. Wait, no, it's 256. Okay.
Yeah, I heard you say 128.
Oh, so I said 256 earlier when I was just taking a wild guess, and then I tried to math, and I failed math.
Oh, okay. I'm sorry, I didn't hear that.
No, you're fine. I missed a.
Okay, power. But if we look at this and we add to it 1, this is all going to overflow, right? 1 goes here, 1 goes here, 1 goes here, 1 goes, this goes here, this goes here, this goes here, this goes here. We go into our next digit, same way as just sort of normal decimal math, and we end up with this number. And this is really just, 2 to the 8th. So that's 256. So the maximum number that I could store in here, since this is 256, is all of these things are 1s. And so it's going to be 256 minus 1. So my largest number that I can have if it was unsigned is 255. So this
because 0 counts.
Yeah, 0 counts. So that's exactly. Not to mention the fact that it would, so if we didn't include 0, then yes, we could put 256 there. But by convention, we start from 0.
But they're like 256 numbers.
Yes, there's 256 numbers any way you slice it. There's 256 that you can have, 256 combinations, I should say. Or do I mean permutations?
Oh, Lord. No.
Okay. Nope. Okay, if I flip these bits, like if I put a 1 or a 0, I've got a total of 256, which is normally numbered from 0 to 255. Okay, so that's neat, except that typically we want to use this last bit as a sign bit. So usually if there's a 1 in this bit, that means that the number is negative.
Can you repeat that one more time? Wait, what?
So let me clear that. Okay, so I've got my 8-bit wide thing, right? So it's here's my 4s and here's my 8s. So if I chop that all up, then typically we reserve this last bit as the sign bit. And that kind of tells us, like, if this is 1, then the number is negative. And if this is a 0, then the number is positive. So
wait, what? Why? How?
Well, because how else can you signify that this number is negative?
Making it bigger doesn't seem to make any sense to me.
Well, if we make it bigger, like if we add another bit here, then we have a 9-bit architecture. So.
No, I guess the way that I'm trying to express this is that if we had zeros, 1 in first, and I guess this is an assumption, but I'm guessing we're reading from right to left. Yes. Or I mean left to right. Oh shoot! Why am I reading right to left?
The funny thing about left to right and right to left is actually that's a big fight in the chip community. So that gets into the way you read it is not really standard either. There's this thing called little endian and big endian, and this is left to right, and this is right to left. So, you're not wrong to be confused about that, but we're not going to get into chip architectures for right now. So I'm going to be following the convention of big endian, which is really handy for while we're teaching because it's the way we write numbers, right? You know, if we write a normal number like 1,000,000, we put the big part over here on the left.
Right. So the more that we add to the left indicates an increase in size.
Yes.
So how come when there's
is a bigger
yes. So even though that's the inverse of like Cartesian coordinates, and that throws all of my poor little baby elementary school math students off, but when we are increasing by moving to the left, how does that somehow translate to having right? If you think about it, like moving to the left indicates an increase in negative. So I've had a lot of students, but why then when our leftmost bit is 1, how are we going Cartesian with this? That suddenly it's negative, or like I feel like my students, I feel like I should go apologize to all of them for being like, it's okay, you'll get it. I'm like, oh
no, it's okay, you'll get it.
Oh boy.
Sorry, you totally set that up. I know. So why do we choose this bit is basically what you're asking. Why are we choosing this largest bit instead of this bit? So like if I was writing this as a normal number, like, you know, 1, 2, 3, 4, 5, 6, 7, 8, then this is the least important number, right?
Yes. If you're saying that's the ones place, then yes.
Yes, ones place. Okay. So I'm just writing it as a normal number. So ones place. That's a good name for it. Okay, and this is the most important number.
Yes. But somehow now we have a negative. That means negative.
Well,
because we put this. Can I just think of it like that's what the sign is? That's
exactly kind of why we do it. So if we were going to make this number negative, where do we normally write it?
All right, fair enough. That actually makes sense. Okay, all right.
So
it's like people have lost their mind, but
it's one of those things. Like the minute you start looking at binary, like everyone just sort of like, oh my god, I don't know, you know. But no. They borrowed this from sort of like how we normally do math. So that's great. So we would typically put that here. I mean, it doesn't really matter to the computer whether we put it on, as long as we all accept the same convention. So we can put it on the left or we can put it all the way on the right, but
we need that indication.
Yeah, we need to. So by convention, it's typically here because that's where a normal sign would show up anyway, in a regular number. And when I'm doing this number, and by the way, we typically break on 3s when we're doing our 1,000 separator in the U.S. world, then it's very fun when you're talking to like your European friends and they're like doing that. And then
with the periods?
Yeah, and then they do that, and then you're like, no, you only get one of those.
That deeply confused me when I played Pokemon, and I thought I had so much money.
Yeah. So okay. So basically, this sign bit was typically reserved in the original kind of architecture. So that meant that how many bits were available to actually represent a number?
7.
Yes. So if I have this as the sign and I have this as my number, which is 7-bit, then what's my maximum number that I could store in 7 bits?
Now we're saying 127.
Exactly. So here's this would be the biggest number, is everything is a 1. And we would just calculate this. We could add 1 to it, and then that'd be the same as this thing, which is, you know, that basically that thing minus 1 is your 127. Okay. Now, this led to a little bit of a logic problem when we were first building computers. And the problem with this is if I just use this bit as the sign, like I've got, you know, this thing could be a 0, means it's positive. So we're going to adopt a convention. And 1 means it's negative. That sounds good, right?
Mm-hmm. Yep.
Well, unfortunately, that creates a new problem, which is what do I do with -0 versus +0?
But what? 0 doesn't have a sign.
Why not? It's right here.
Well,
we just said that's the sign bit. So if I set all these other bits to 0 and I put a 1 in front of it, I've just written -0.
But Okay, hold on. I'm
yeah, we just
brain
agreed.
is processing.
Yes.
This seems like a problem not of reality and more of kind of like convention and semantics.
Well, if we I mean, what other convention could we adopt to indicate sign?
I mean, so no, it makes sense to have like the
we got to burn a bit.
sign, but we can say that -0 equals +0 and that they're the same.
Okay, if we did that, then we would probably have to increase the number of logic gates we use on the board massively, because now we have to deal with a register, a memory location. All of the parts that make up a computer could either have positive zeros or negative zeros, and those are still the same. So even though this bit pattern is 0, this bit pattern of all zeros is also 0. So I would have to, if I was building this in logic, I would have to say this bit doesn't matter if all of these are 0. Otherwise, this bit matters, and this is, do certain things, and then otherwise do this, and then, we have to be careful. So suddenly you're building like a lot, like you're adding a massive number of logic gates. So we could deal with this convention of -0 versus +0, but that's a little scary when you're like implementing this thing. Have you seen like these like old school logic gates?
I have not, but I would love to.
Okay, so like this is a not, and this is an and
yes. Okay, actually, I have a little app on my phone that is all of this trying to teach me to like read circuit diagrams, and it's really cute. And
back in the day,
terrible at it.
We had to actually like do this, right? Computers still work in terms of these logic gates, even though, NAND gates became pretty popular because you could do pretty much everything if you were using a NAND. But so yeah, this is exactly what Strophium is alluding to in the chat. So what do we do with this -0? Well, another thing that we could do is we could just avoid this situation.
How? How do you avoid that?
Well, we avoid the situation, but yeah, sure. Do now?
Yeah. Do you mind?
No problem. Chat. I'm just gonna chat with you for a minute.
Give me 1 sec. Sorry,
yes.
friends. I'll be right back, and I'll mute myself on Discord so dog bark won't interrupt.
No, please go right ahead. So we have some dog walking that has to happen. So, all right. Well, I'm just going to go back here and show you this wonderful tool in the meantime, because it's totally awesome. Actually, you know what? while we have this moment, I can totally show you this thing, which I think is super cool. And I really can't wait to get going with it. We're going to be literally doing bits very soon. And I'm very excited about all that. And this is kind of fun because these are your, sort of data pins. Get a little bit closer. So this is a pretty advanced chip. So we have like and for those of you that missed it earlier, this is the 9-axis chip. So we have magnetometer. We can really tell which way something's pointing. So if we wanted to take, say, this power glove, and we wanted to make it like really work awesome. Yes, by the way, Miss Sagittarius, this is an Adafruit part. And no, they did not sponsor me. I had to buy this thing. I think Adafruit is super cool, but I'm not on their payroll in any way, shape, or fashion. So, but what's really nice about all this is like, for somebody with my meager soldering skills, you don't have to really like get into this too much. So if we kind of come in here a little bit closer, and that is what we want, then you can see all these like really fine pins that are on this board. Like I suck at soldering. So binding this chip would be like a nightmare to me. So are you back? Did I hear you? Oh yeah, you are back.
Yes. Sorry, I didn't want to interrupt.
No, it's fine. I just got a little carried away with the
when dogs need to go out,
No, that's
hustle.
Totally fine.
or disaster happens. So
all right, so let me just kind of wrap this part up, which is that basically what we did was we wanted to avoid this situation of -0 and +0. So we adopted another, and we didn't want to double the number of gates to deal with all of this stuff, logic gates on the board. So instead, what we did was we adopted this kind of a little bit crazy convention. So we still keep the notion that this is kind of like the sign bit, but now it's in quotes because it's sort of a sign. And the way we calculate this bit is we basically invert all of this stuff.
What? Wait.
Right. So
okay, sorry. It's like that moment of like every time I learn something new, my brain's first response.
Totally.
Wait, what?
Yeah,
like, hold on, processing.
That's the pull the rug out.
Huh?
So basically what we want to do is we want to have our number. So before I was trying to say like, okay, let's go from 127 to, negative 127.
Mm-hmm.
And that left the problem here in the middle that we had this 0, and then we go over here and we have negative 0, which we don't want. Well, why don't we just throw out negative 0, because nobody really wants that.
Mm-hmm.
And that leaves us kind of the question of like, where do we tack it on? And that's, this, by the way, was not at all what I was planning on talking about tonight. So I apologize. But
the rabbit holes are the best, though.
Yeah, we've completely gone down the rabbit hole at this point. But basically, we can stick it on one end or the other. So we can say, all right, this way you can go to 128, and that way you can go to negative 127. Or this way you can leave it at, oops, I'm totally off my screen at this point. So this way you can go to 127, and that way you could go to negative 128. So those are basically our two choices.
How do you choose?
And the way we choose is we just sort of slide everything over. So
you're joking.
No, it's a little bit more complicated than that, but just because we want normal math to work, because like if we take one of these things and we want to reuse the same circuits. So like if we, instead of just encoding it like we would naively, which is we just use this bit to represent the sign, then, one would look like this, all those zeros. And if I wanted negative 1, we would think that this would be the 1, right?
Yes.
Okay, well, this ends up kind of violating math a bit, because what happens when I add a negative number with a positive number?
It depends on the size of the numbers.
If I do like 5, right, exactly. If I do 5 plus negative 2, if I do 5 plus
3.
negative 7, I mean, this is going to wrap into the negative space. This is going to stay in the positive space. If I invert that and I do a minus a negative, then really I'm doing the same thing as adding. So this all kind of like, I want to keep it so that all of this stuff sort of works like by default. And that's basically the gist of why we're going to do something crazy. What we're going to do...
This is all crazy.
Yeah, this is all crazy. This is actually how the computer really works.
It just... So I think the thing that I'm struggling with is decided to shift one way or another, but that
you broke
is
up
there
there.
No standard? Oh, I'm sorry. So I guess describing... I love, of course, yes, my math brain is all on board with getting rid of the negative 0 because that made me sad in the first place. But and extending the range in either positive or negative direction makes a lot of sense.
Sure.
However, I feel like, should it not be standardized?
It is.
Right? Okay. So it's not that it's user's choice. It's that a decision was made.
This is the decision kind of like back in the 70s. So
okay.
And basically what they ended up doing in order to preserve all of these operations that I'm showing you, I'm doing like kind of the fast version of this, like the full lecture would be really complicated, but it's not too much worse than what you're seeing right now. But I don't want to go into that level of detail, but basically what they're going to do is they're going to flip all of these bits. And if you do that, then your basic properties work fine. So this stuff that I was showing down here, like 5 plus negative 2, 5 plus minus 7, all that stuff, they'll work with just a normal add. Like if I just keep my normal add rules, then flipping all these bits sort of makes that work.
And when you say flip,
yes,
are you saying invert or are you saying reflection?
I don't know what that means.
Like, are you saying mirror it? Like you are flipping it over a horizontal or a vertical axis, or are you saying invert each bit? Like, do the zeros become ones, or does the number become mirrored?
the zeros become ones.
So it's inverted.
Yes. So to get a sign, like say I want to flip this thing, then basically, so it's called the 2's complement that we're talking about. And the way it works, I mean, I can talk about it at the bit level, like we're talking, there's some nice logic gate properties, but it's a lot easier to calculate if you just look at, like, say you have a number and we're going to call it num. So it could be nice. Any number, right? This could be like 5 or this could be 7, but it's going to be something positive. If we want to get the negative version of it, then the way we 2's complement and avoid this, like, you know, 0 thing and all that range stuff is we basically take 2 to whatever power this is, like whatever position this is. So this is like position 0, 1, 2, 3, 4, 5, 6, 7. Okay. And so this would be the 8th location, which is not part of this number, but that's how many bits I have total if I count them, right? So that's 8, right? 4 and 4. Okay. So I take 2 to that power, which would be 2 to the 8th, and I subtract whatever this number is.
Okay.
So
128 minus 5. So 120.
Not 28.
256.
2 to the 8th.
Yeah, not 7. 256. So 256 minus 5, 251.
Yes. And that is actually what's represented. What's nice about this number is I can tell because it's a high number. It's anything above 128, well, 127 or anything greater than 127 has this last bit flipped. So by convention, those are going to be negative numbers. So I can tell right now that this is a negative 5 if we did the math right.
Okay.
Okay. And that's called the 2's complement, and complement in like the sense that this 5 and negative, this 251 and this 5 are complements of each other in that they both add up to 2 to the 8th.
Say that one more time.
So we call these complements of each other.
Complement. When you say these, which 2 things are the complements of each other?
5 and its 2's complement is 251. Doing it the way we just calculated. If we add these together, we get 256. Right?
Okay. All right. Yes, I'm following.
Which is 2 to the 8th, which is, if I unwrap it, it's, you know, there's our 2 to the 8th minus 5.
So this is probably a really silly way of thinking about it, but visually what I'm imagining is when you first were describing, we have these kind of 8 bits, and as we're sort of progressing and we're adding ones, things are getting bigger, right? So it's almost like a number, but as we move to the left, things get bigger.
Yep.
Well, now because of the negatives, they've decided to almost split it in the middle.
Yeah.
And so you have kind of mirrored halves, right?
Yep. Yeah, those are the complements.
All right.
And then we avoid that negative 0 thing.
Yes. Okay. That makes actually, I think I understand that.
And it actually works. So I can add these numbers together and, you know, it'll stay in the right thing. So if I have something like, you know, 251 and, you know, I add it to, you know, 3, it's going to stay negative.
Right.
So that's going to end up being like 254, which if I flip that to 2's complement, which is 256 minus 254, I end up with, this is really the representation of negative 2.
Negative 2, yeah. Okay.
Which is cool. So that's the same as I took this 251 was negative 5. If I add 3 to it, I end up with math working. And that's why they did it.
Oh, that is so cool. All right. Okay. I think my brain is, I'm like tenuously understanding this. I think
it requires a deeper lecture. I'm sorry about that. We're trying to
no, this is really fascinating because I mean, if you mathematical problem of how do you implement the full range of well, not full, but like, you know, a limited set of both positive and negative numbers without duplicating the split.
Yes.
The split point.
Exactly.
Right?
And
that's interesting.
The other constraint is we want math to still work.
Well, yeah. And so Oh, people are so
Otherwise,
smart.
we would have to double our math unit. Like the math unit on the chip would have to have how to deal with positive numbers, how to deal with negative numbers, how to deal with one positive and one negative, how to deal with one negative and one positive, right? That would increase the amount of logic on the chip a lot. But
yeah, that sounds like my approach in Python of just try accepting everything.
no, which is fine in Python. But, like when we're talking about the metal, like that's going to directly turn into cost, right? If we make the logic that complicated, engineering time is going to go up, chip failures are going to go way up, bugs are going to go way up. You're talking about, chip fabs, you're usually talking millions and millions. This is very expensive stuff. So they had a big incentive to try to get this right. So,
this reminds me a lot of when I started first playing Minecraft, and I think it's a wonderful game. It's beautiful, and I was so excited to just collect random resources and build a house and not die. And of course, this was many, many years ago. I haven't played in years, but went and Googled Minecraft, and lo and behold, people have built computers in it. And I'm sitting there like, okay, yep. I barely am surviving the night. I think farm, I've got some sheep, I'm really proud of myself, and someone's built a computer. And so I think that's almost what this reminds me of, is kind of that I'm really proud of myself for sort of writing in Python, but underneath it is this very, very complex but fascinating underlayer of.
Well, we're getting closer to the metal now.
Yeah, this is really interesting, because when you first introduce plus or minus zero problem, I've been thinking about it as you've been talking, like, how could you fix this? How could you fix this?
Right.
Like, over and over in my head, how do you get away from this problem of doubling the zero? And so it's really fascinating to consider instead, well, basically a number line, but using sort of your bit storage like a number line, and splitting it in the middle and having reflective. That's really interesting.
Right. But we keep the low numbers acting the way numbers work, right? So everything that's less than 128, which basically is all the stuff that doesn't have this, this top bit set, it works the way we expect it to work. So like 0 to 127 is exactly like how you would expect it to be stored in memory. So, 1 would be shown as all zeros and a 1. 2 would be shown as all zeros, and this gets a 1 and that gets a 0, and so on. I should really clear this if we're going to do that. But
do me a favor and do a positive number minus a negative number, because I'm wondering,
sure.
Like this is fascinating, and I keep coming back to these students that I've tutored in math, who are elementary school students deeply struggling with the idea of a negative number. And I almost wish that we taught computer science maybe like way earlier, because I think this actually would sort of make a lot more sense, is being able to show them that I don't know how to explain it. Like it's I usually go with a number line when.
Yeah, I would do it graphically, probably to somebody who hasn't seen it.
But then it's also like this idea of minus and negative becoming a positive. Just
that's what really I learned as a heuristic. Yeah.
Right? Is that you take the two minuses, but it's quite interesting that when you convert that to their respective, I guess, bits or whatever, that if my brain did it correctly in my head, it works.
Oh, you want that as a binary example? I'm sorry.
Yeah, I'm sorry. Like, no, okay, yes, I know how to.
Okay, well, I don't know. I was trying to find different ways of writing it. I'm like,
okay.
Yeah, so I got a little animation. You can take this minus and you can kind of move it over here, and then it moves on top of here, and you get a plus.
Please help me with elementary school math.
I'm sorry, I totally misunderstood your question.
I should have specified. I'm sorry.
Okay, so I'll take the same example because I already wrote it out. So I was doing 5 minus 3. So the first problem that I have is I have to represent these in binary, right? So 5 is actually it's a 4 plus a 1, and 3 is really the minus version of, a 1, a 2 plus a 1. These are in powers of 2. So I'm doing like one way of converting to binary, which is going to be, we need a 1 in the 4-bit and we need a 1 in the 1-bit. So like if I've got, if this is my number, so 5, fortunately, like, so this is my 1 placeholder, and this is my 2 placeholder and this is my 4 placeholder, then this is going to be a 1 in the 4 plus a 1 in the ones digit. And I put those together and I end up with a 5. So there's my 5 representation in binary. This can also be thought of, this is the 2 to the 0 place, this is the 2 to the 1 place, this is the 2 to the 2 place, this is the 2 to the 3 place, on and on.
Okay, that one makes more sense.
Yeah,
Yes, okay.
Well, this is more analogous to probably how you think about normal numbers, right? If I do 1, 2, 3, 4, then this is really the ones digit. So, but we're in base 10, so this is 10 to the 0. And this is...
Wait, no, that's not... 4 is not 10 to the 0.
Well, no, this place. Sorry. Just where the 4 is occupied is...
Oh, I'm sorry. Okay, yes,
yeah,
yes. Ones place, 10's place, 10 to the 1. 10.
This would be 10 to the 1's place. This would be 10 to the 2's place. This would be 10 to the 3's place. This works for any arbitrary base, by the way. You take the base and you take the exponent is basically how many digits it is from the 0. So...
Right.
So if I take that as like, this number could be written as 1 times, I'll write it out, like 10 to the 3 plus 2 times 10 to the 2 plus 3 times 10 to the 3, 10 to the 1 plus 4 times 10 to the 0. Okay, and if I do that, I end up with 1,234. Still good?
Yes.
Okay.
Yes.
So using that representation, we can do that with base 2. So this is base 10 or decimal, which is the reason why that format specifier is a D, %D.
Okay, yeah.
Versus like this thing over here, which I'm composing out of powers of 2. So this is 2 to the 0. Why are we using 2? Because then our logic gates are going to be minimalistic. I mean, that's kind of the reason we started with binary in the first place. We could try to build a computer on base 10, but that's a lot of circuits that I can't solder that much. Okay, so converting this 5 over to binary is sort of the matter of like which powers of 2 add up to making 5. So in this case, it's a 4 plus, a 1.
Mm-hmm.
Which
so like
is
a power of 2, power of...
Yeah, this is the power of 2 digit plus the power of 0
1.
digit.
0, yeah.
So my binary representation of 5 is 101. Okay, so if I do that minus 3, how would I get 3 normally? Well, as powers of 2, that's a 2 to the 1 plus a 2 to the 0.
Right.
Which would be this
so
is
just 1 1.
This is 1 and that's a 1. We're going to put a 1 there. So 3 is going to be 1 1. And now I need to do this 2's complement business. So working in the decimal space, I would just do 256. If we're working in 8-bit numbers, then I do 2 to the 8th, which is really also known as 256. And I subtract 3 from it, and I end up with 253. And if I represent that, it can be represented the way that Strophium actually mentions in the chat. So all I have to do is flip all these bits and subtract 1. So, right. So basically that's going to be 0, 0, 0. This would be positive 3, would be 0, 0, 1, 1. And if I just flip these bits and I subtract 1 from it, then I should end up with, that doesn't look right.
No, there's 2 zeros at the end. If you're flipping them, right?
That's what it is if I don't do the subtraction, right?
Yes.
That's just flipping all the bits.
Yep.
So I have to get 253, which is, wow, arithmetic, huh?
Sorry, I really put you on the spot. I appreciate it.
No, it's okay. I mean, I normally don't do it this way. So I'm used to just calculating what is 253, and 253 is a 128 plus, a 64 plus, which is actually all of these things. And if we just check our math, then this, it is -1, right, Strophium, doing it this way? So I would just have to do 0, 1, 0. So I think that's it. But quick way to do that. I mean, well, hey, we got C. We can. Why don't we have C do it for us? Did I lose you?
Oh no, I'm here. Sorry,
okay.
I thought you were explaining how we make C do that for us.
Because no, we're beyond that. Now we're coding.
Oh boy! All right, so we're going back from. Okay. Yep.
Yeah, I mean, so all we need to do is we just need to be able to output binary. So we'd have to code that whole routine, wouldn't we? So rather than do that, let me just check the format. I was just working a lot in Python, so I forgot the format specifier for binary in C. So I'm just looking at the printf man page, and we'll see this thing.
So quick question.
Yep.
We've been asked by the chat if these videos have been recorded at all, because folks want to kind of start from the beginning and follow along.
Yes, I need to talk to you about your feelings on posting them.
I'm fine. You're good. I've been very well behaved. I have not. You've been the one to actually swear, not me.
Okay.
So I think I've behaved admirably.
Fortunately, that word, which I'm not going to mention, is still TV safe as far as I'm aware. So I think we're okay there.
Definitely more well behaved than I normally am on my stream. So totally fine.
No, but assuming you're okay with all that, then I could post that.
Yeah, you're fine. Of course.
Okay. So yes, the answer to chat, we will put these on. We'll put these on YouTube, but let's get through the rest of the lesson. Okay. So
I feel like I'm gonna start having to solder something. We're just going so deep. I love it, but I'm like, should I
we could totally solder.
Let's do this.
Why don't we
let's build a computer.
I'm gonna just cheat and punt on it by figuring that we can use hexadecimal, because if I use hexadecimal,
like in The Martian,
then okay, we're getting 32-bit math here, but so I'm jumping a little bit ahead of what I was going to say, but unfortunately. But the important part is going to be these last two digits, which correspond to 8 bits. So there's the answer right there, which is FD. And D, borrowing, I just wanted to check the math because I really haven't done this in C in a while. But so this is normally written as 0xFD. I'll write it in uppercase, hex. And F corresponds to 1111, and D is a couple behind it, right? Because DEF, which is our -3. So E would correspond, just to break this out because I'm kind of talking over it. But if F is correspond to here, let me clear all this. If F is 1111, E is 1110. Then D is 1101. So that's it.
Why? I'm sorry. So I went with the classic just alphabet cipher, right? So I'm like, okay, if I'm sitting down and using all of the things that you've taught me and I want to encode the alphabet, I would think I would just kind of use, like all zeros is maybe A. I don't know. All zeros and then 1 is maybe like B. And so how have we gotten what is the equivalent of four ones, which is like what, 2 to the 4, 2 to the 3, etc., is somehow F?
Oh, because that's hexadecimal. If I wrote the whole, the answer to that is actually in the definition of what hexadecimal is. So
that's basically, by the way, thank you very much. That's my hand wavy answer. Who in Python is when he asks me questions about why certain memory things are happening. I just and this poor child doesn't even know what that is or know why I'm telling him that. But thanks to you and our first C stream, I'm like, oh yeah, it's probably just because of hex. That's oh, I don't know really, but it's memory thing, so probably.
Okay, so here we'll just count it up. I mean, this is literally okay, so this is all zeros. I'm just gonna stop the slashes for a second. This is 1, This is, I'm just counting all of our 4 bits of binary. Right?
0 to 1. Yeah, okay. Yep. I'm following.
So
yeah, and then
I
0.
add a 1 to this and it goes to the next digit. So
0, 1, 0, 0.
0,
Yep,
0.
okay.
I add another 1 here. So 0, 1, 0,
It's not that
1.
hard.
I add another 1 here. It overflows. 0, 1, 1, 0. I add another 1 here. 0, 1, 1, 1. I add another 1 here. I get 1. See, there's our 8th bit. This is actually our signed bit, by the way, in our 8-bit example. But we'll just keep going. So this follows from here on. It follows exactly the same pattern it was down here. So this was, 1 0 0 1 1 0 1 0 1 0 1 1 1 1 0 0. And if I keep going up from there, I get my 1, my 1 0, and my 1 1. Okay, so I wrote this correctly. This is, D is this thing, right? So why are we using hexadecimal? Why are we adding these extra digits to our number line? Because if I do this, I end up, so with these 16, they're not called digits, but let's call them hexits.
Okay.
Even though this is has a funny history, because if we do that in Latin, anyway.
Yes. Let's not do it in Latin.
Let's not do that in Latin.
I've got 5 years of Latin under my belt. Teenage.
So it turns out we flip over to the Greek and we use hex.
Let's say Greek. Yep.
Instead of the other word. And yeah. So why do we use hex? Well, it's because this very quickly represents 4 binary digits. Right? One of these numbers from the hex world corresponds to 4 of these binary numbers.
What?
I know. Sorry. I just you say things sometimes and I don't know if this is just the lack of caffeine that happens at 9 p.m. at night or brains. I'm sorry. What did you just say?
That is the important part. So I'm just going to write a few of these. So let's just do, if we're writing out 4 binary digits. Okay. So, I mean, maybe it's better if I actually just do a whole chart. Well, if we're going to go that much to the whiteboard. Sorry, Chad. I didn't plan on getting this far down this
So
route.
I will tell you this as a consolation. This is unfortunately a side effect of teaching. And I found this out the hard way in graduate school when I was in my stellar astrophysics. We were discussing how nuclear fusion occurs in the stars, and I kept just asking questions. I was like, okay, well, yep, I understand that, but how does that happen? And the teacher would explain. I'm like, okay, but how does that happen? And I kept asking. And finally, my teacher kind of loses it a little bit and is like, we don't know. Okay, we don't know. That's the subatomic level, and we don't know. Okay, we just don't. And I was like, oh, I'm sorry.
Oh, we can know. We can know at the subatomic.
Everything is from first principles.
Now you're really speaking my language.
And ones.
I'm a registered nuclear physicist, Department of Energy. So
nice.
we absolutely can know, and I spent a good little chunk of my life knowing exactly what you were just talking about.
I mean, we were getting into quantum chromodynamics, so sort of the forefront of the forefront. And at one point though, I'm probably on one of your lists of people to watch, because poor quasi baby Jess was Googling all this stuff, being fine, if my teacher won't tell me, I'm gonna learn myself. And ended up on some restricted website with all these alerts from the US government being this is protected and restricted information, you don't have a clearance, blah blah blah. It's I panicked, of course, as an early 20s person, because I was I just wanted to understand how stars work. But no, so my point was just, if ever I go too deep, you can kind of just say not now, and I will pause the brain. But
okay,
generally speaking, it helps me a lot the more fundamental we start, because then that knowledge is really great and I can build from that, but it's how my brain works. So if ever you're like,
no, it's totally fine.
I don't want to spend all this time talking about binary, like just wait.
I mean, if you don't mind the fact that I didn't prepare this part of the lecture.
This is awesome. Are you kidding me? Like I've always wanted to learn binary, and I was wondering how Loaf, Bone, and Chat could whip it out so fast when we were doing puzzles and stuff. And now this makes sense.
Yeah.
The math makes my brain happy.
No, that's fine. I mean, so basically I'm just writing a chart here. Like this is just normal decimal numbers here on the left. And this is 4 binary digits in the middle.
Okay.
And what would this be in hex? So here in this 4-bit representation, we're seeing like all of the possible combinations of 4 bits, right?
So we're so why have we gone somehow from 8-bit to 4-bit? And I'm sorry if that's a stupid question.
No.
I just like
we'll get to
we
that
used to have 8 and now we have 4.
Let's stay with 4 for a moment.
Is that where hex comes from? Because honestly,
that's
like
exactly where it comes from.
Okay.
That's exactly what I'm showing you.
We're limited in terms of our memory and limited to
No. It's the same amount of memory. So the number of bits doesn't change no matter what the representation is. But what we want is, I've just written, if we do this 4-bit thing, this gets kind of obtuse by the time I'm talking about, like, do you really want to write out like 1001? I mean, that's a lot of like screen real estate. Like, what if I do a 32-bit number? I mean, that's...
Oh, Lord.
This is just 4 bits.
Hold on, I can barely handle 8. Let's not go.
I mean, so like if I here's like 8 bits, here's like 12 bits, and here's 16 bits, and I'm only halfway there.
Oh man. Okay.
Whoa, we're halfway there. Whoa, living on a binary prayer. I mean, we're just like this. I'm writing this stuff all day. I'm singing Bon Jovi at this point. Like this is crazy. So, all right, wait, hold on. Sorry, I got a little carried away there. So, I was only halfway there on 16 bits, right? And then by the time I'm getting to 32 bits with another 16 bits, I've written a lot of friggin' digits.
Now I'm terrified of 64.
Like, yeah, like you try to write 128 bits. Like you're going to be writing bits all day. I mean, this whole thing is going to go crazy. So that's basically the problem. So I want a compact representation of this thing, right? So that when I'm actually looking at like 32 bits, which is, a lot of processors are 32 bits. So these days, 64 bits. When I'm looking at that, I don't want to see all this. Right? I mean, this is like going to be a crazy amount of ones. You're going to be like, look at it, be like, is that a 111001101? I mean, I'll be saying that all day, and we won't even know if we said it right. Like I could totally have flipped a 1 in the middle there somewhere, and it's very error prone, right?
Oh boy. Okay. So
how do we solve that?
Like,
I mean, you're a linguist. We need a more compact representation. This is a very non-compact representation.
Right. And I'm guessing the answer is to somehow represent 4 bits, because that's what you circled over there. But yeah, I guess I don't understand how we get from happy math land, which makes a lot of sense to me, where, the binary actually makes sense for the first time in my life. Like, I get this. And now bits aren't scary and they're not just random numbers. Actually makes sense. But when you turn instead to having, say, a codex for English language orthography, your A's and your B's and your C's, etc., I still don't understand why it's not just a basic alphabet cipher. Why we don't just say,
well, it is an alphabet cipher. We take this thing over here, this is 10, right?
Mm-hmm.
Well, actually, this is a 10 because we're in base 10. This is decimal. But I overflowed when I went from 9 to 10, right? I moved to the next position.
Yes.
Okay, that is not what happens over here on the binary side. Right? I'm overflowing every single line.
I mean, because you can only count by 1 essentially. So every even step you're.
Yeah, every other line I'm overflowing. So that means that this representation, and plus from a symbol perspective, like you just mentioned, this is a lot of symbols to convey very little information. right? I'm only using a 1 and a 0. So my entire cipher is composed of 1s and 0s doing it this way. But how can I compactify that and still preserve this notion that it overflows position the way that I normally think? Like, so here it overflows from 9 to 10. It goes to the next digit, right?
Okay, yes.
But that's not what happens in binary, because it would overflow up here on the 15 line.
Okay.
Right, because the 15 line, 15 in decimal corresponds to 1, 1, 1, 1. So if I add one more here, I end up with 1, 0, 0, 0, 0, right? I overflow to the next position.
Right, and we're limiting ourselves to 4 bits.
Right. So that's what this is like. If I only want to use, how many symbols do I have on the left? 1 through 15. I've got 16 symbols, right?
Right.
Corresponding exactly to 4 bits. So that's exactly why we invented hexadecimal. So all we had to do was extend our numbering system. This was the 9 line. And all I had to do was add in a symbol that represented 10, which was this A. And then I can add in B, C, D, E, F. And this is this corresponds to 15, because after that, I go to 1, 0. Okay, do you see that? So I'm talking about, like, how do we correspond to 4 binary digits? 4 binary digits is represented by 16 symbols. So we just named these symbols that normally overflow. We named them like this stuff over here. We just started using letters A through F.
Okay, so this is funny story, right? This is interesting, is that I wrote a hex to whatever normal people number conversion, sure. Because when the Hubble Space Telescope returns your observations to you, it returns it to you as observation underscore a hexadecimal number or whatever. And so I was dealing with random letters and numbers and totally confused. So I remember kind of some of this when I was trying to figure out how it works so I could convert it to decimal and have like, oh, this is, my 98th galaxy that I was looking at, but this is some weird convoluted string of numbers and letters. I guess so. I think the thing that is tripping me up, to be honest, is that we've gone from a system that made mathematical sense, where you are almost talking about the place value of a number by moving from right to left.
Yes.
And representing various numbers increasing in their absolute value as you move right to left. That made sense to me. And then, of course, as we try to mathematically have a representation for characters, we somehow decided to truncate things at 9, which makes intuitive sense because really a 10 is just a 1 and a 0.
Yep.
But that's not how it works in the binary because things are kind of stacked. So that's where I'm getting a little bit tripped up.
Oh, no, that's fine. And actually, I'm going to go back to Strophium, a comment that Strophium made, because this is actually what it comes from. Why did we...
Imagine if your finger's heading...
No, and that's important, because that's actually where we get counting from. Why did we choose 10 symbols?
Right.
I mean, that's arbitrary, right?
Yeah.
We chose it.
That literally has to do
with... We
with
even call them digits. What are your digits?
Yeah, it's one of the sort of hilarious, pub arguments between a mathematician and a linguist is like, we're the, mathematics is the basis of all things. The linguist is like, well, why do you call them digits? Right? It's like, it's a convention.
I haven't heard that. I need to go to the pubs that you're in. There's no question from hearing this, because I would love to go to a pub like that.
Well, especially when having once been a linguist and sort of converted into more of a math, well, it's a long story. But anyway, being both, it's fascinating, but it is entirely convention. And so, there are lots of amazing science fiction novels that cover what happens if we encounter a species that has decided on base 8, base 12, base 11. Like, how do we deal with that? And how do we communicate? Because whether we like it or not, math and language are inextricably linked. And so
No, this is important.
Yeah.
This is not theoretical.
Yes.
Like we call them digits for a reason. I mean, they were the digits on our fingers. We learned to count with our fingers. We learned to do our math with our fingers. If you chose to count with your toes as well, like say the Mayans did, what base would you choose for your numbering system?
I thought Mayans. Okay, so again, sorry, chat. I was my linguistics. So,
it's not hypothetical about like another species. I thought
Mayans were base 12.
No, I'm pretty sure they're base 20.
Are they base 20? Okay, no. Then that's my mistake. Vague. We're talking like over a decade.
I just want to make sure I got the right culture. 100% I know. This actually came up in my history of math course. I haven't looked at it since
that's
then.
Cool. Because I know there's one sort of like proto South American culture that did base. I thought it was base 12 or base 16. But that makes a lot of sense to have base 20 then.
No, I remember. I'm pretty sure it was the Mayans, but it could be another culture in that area. But it's called vigesimal. I mean, because literally you're decimal is we're borrowing the Latin stem here. So staying with Latin, we can go vigesimal.
Yeah, we've got chat following along.
And like, that we can count with our. This is just using our fingers because we got 10 of them usually, in most cases, and this is using fingers and toes, right? So there's no real reason why we chose a particular base other than we just happen to have that many digits on our hand. So when we're talking about binary, there was something else going on, which is the number of logic gates that we had to operate on, right? Because we didn't use decimal because it would increase the number of logic gates quite a lot. And when we were building on this base 2 logic, we ended up saying like, okay, this is going to get really messy because base 2 does not naturally divide into base 10, right? I mean, despite the fact that 10's an even number, like there isn't, how many binary digits would be in a base 10 number? And the answer, by the way, is on your screen.
Oh, well, I was trying to do it in my head.
You could do it in your head, but I mean, it's right here on the 10 line, right? So this 1010 is the bit pattern for 10. But that means that I'm wasting a bunch of bits because I'm never going to set this thing to like 1110. This would be an illegal bit pattern because that's more than 10.
Right. Okay.
So that's kind of why they said, okay, well, the real problem here is the fact that if computers are counting on their fingers, they only have one finger.
Well, you know what, computers, okay, well, GG, I win. There we go. I think, so Strophium, this is why Strophium says this is why quantum computing is so strong. Since transistors can only hold on-off states, binary values end up being these long strings. The more values you can represent in a single digit, all of a sudden your operations just get way faster. So, Strophium, you and I should have
I think that's a
stream conversation about
yeah.
quantum computing, because my favorite class in graduate school was quantum mechanics, and that's the physics that makes me happy. That feels very, very, very far away from what I am doing right now. So we should talk about that some other time. But
definitely getting far from two's compliment, but just to fault lines comment right above it.
Let me see.
The same number is represented. It's the same number. It doesn't really matter what your representation system is, right? So in the case where I was doing, if I'm doing binary or if I'm doing hexadecimal or if I'm doing whatever, I mean, like this number that I think of as 5 in ordinary terms corresponds to, this is 2 to the 2 plus 2 to the 0. So I need a 1 in the 2-bit and I need a 1 in the 0-bit. So if I put that out as a series of bits, then this would turn into, well, this would be a 1.
In 4 bits, 0, 1, 0, 1, right?
Yeah. This would be a 0 in the 1-bit, it'd be a 1 in the 2-bit and a 0 here. So this would correspond to 5. But these two representations both mean the same number of things. I mean, like if I was counting triangles, it's that many triangles, right?
I think I'm still kind of I'm tripping up on the like the math makes me happy, like the numbers land, that's the happy place. The second we step over into somehow trying to represent characters, so string parts, string bits in numbers, I start to struggle because it seems very arbitrary to me why we've decided on either 0 to 9, because like again like we just talked about, that's a human convention, or that's not a human convention, excuse me, that's a very like specific human culture convention, right, of going 0 to 9 and then starting over. And why not make it some multiple of however many letters are in, I forget. I know a few alphabets, so bear with me. Like, I think it's 26. We talked about this earlier. 26 for English, I think. Yes.
Yes.
Why not make it some sort of like multiple of that, like 13? Like, why? Because it's very arbitrary. The second that you move into we need to start over when we get to 9, because a matter of convention and less a matter of like, so why is, if hexadecimal is the thing we use to be able to represent characters, why did we not pick something that's a little bit more rational?
I would say that it is very rational, but the rationality is entirely based on understanding hardware theory, which is not really something we should get into.
Yeah, no worries, and that's fine. You can...
No, I mean, there's a very rational reason why they chose binary. I mean, it has to do exactly with logic gates. I mean, because they were using 2-state logic gates, so you can do things.
No,
like
I mean
this.
the choice of binary makes sense to me. That's not, I guess, the choice of how we defined hex.
Oh, well, I'm showing you. Basically, the computer's operating on binary. So because we don't want to write out these long strings of zeros and ones, we said, all right, let's just take 4 of these things and compact it into a single digit from 0 to F. And that's it. So you can think of hexadecimal as just a compact representation of 4 binary digits.
So, okay, hold on. I need to give me 1 second here. So that's... Did we say that ended? I'm sorry, I'm like having a small brain fart. So
that's fine.
It goes 0 to 9.
Yep.
And then A to F. So
yep.
That's a total of 15. Right?
Yep.
So
well, plus 0.
That makes sense. Yes. And that makes sense to me. Like 15, I'm sorry, not 15, the number of digits.
Yeah, which would be 0 to 15 in decimal.
Right. And okay.
Yeah, so if we use that compact symbol thing, then I can represent, using this hex, I can represent 4 binary digits at a time with a single symbol.
Mm-hmm.
Make sense?
I think so. I think I just don't know why we didn't just... Why did we switch to A then?
Oh, like why did we choose A as the next symbol?
Yeah, why didn't you just go 0 to 15?
Because 15 doesn't fit into a single digit.
I see. Okay, so the idea is to take what is represented by 4 digits and represent it as a single digit. Got you. Okay.
In one symbol.
So I've been stuck on, I thought, got you. Okay, so my brain was going down the, again, linguist hat sort of street, where I thought the goal was, how do we take binary and then represent the English alphabet? And I was like, this seems really asinine.
Oh, that's
like,
an entirely different conversation.
Right. And so you kept telling me, we go to 9. And I'm like, why not just start with A? I'm so confused.
And then yeah, that's this totally different.
So much more sense if we're trying to compress things.
Yeah.
I got you. Okay, we're fine. We're on the same page.
That's it. Whew. No, that's totally fine. We took these 4 binary digits.
The brain is slow today.
No, it's totally fine. Hey, you're getting over COVID, dude. You're totally
I'm gonna, that's gonna be my excuse for
you gotta buy for me.
Like December of this year, and I'd be like,
no, I mean, so like just looking at this thing, we can compactly represent, 4 binary digits with 1 hex digit in a single position. right? So I don't have to overflow. So 15, I could represent it as 15, or I could represent it as F.
Right, but the whole point is to take the breadth of numbers represented by 4 bits and have 1 digit.
Yeah, because otherwise, what am I going to do when I get to like, you know, what do I get? What happens when I get to 16? So if 15 corresponds to, I mean, we'll do it your way. Like let's say we didn't use hex, so 15 corresponds to 1111, right?
Yes.
Okay.
Yes. Mm-hmm.
Now, how are you going to show 16?
0, 0, 0, 1 plus 15.
I mean, it's no problem in binary. It's just, you know, 1,
yeah,
0, 0,
I mean,
0.
that's like, yeah, we add another bit, but if we're stuck with
we're adding
4,
another digit because we invented positional math, right? Because back in the day, we used to do like, this is 5, and, you know, this is 3, and this is 10, and this is 50.
Yeah, we're going back now, old school.
And this sucked because what's like LVXI plus IICM? You know, like, I don't know. That's going to take a while, right? Like that's totally how it used to work back in the day when we chose arbitrary symbols. Instead, we moved to positional math, and we said each one of the positions of the digits.
Thank you, Arabic, by the way.
Yeah, that corresponds to, yes. It's funny. It's not Arabic. It like people talk about like Arabic numerals. They're not Arabic numerals. Like Arabic numerals are an entirely different thing.
I know Arabic numerals.
Yeah, they don't look at all like Latin numerals, but we definitely stole the positional thing from it. You know, like we were like, oh, okay, this looks pretty good because I can actually calculate 15 plus 5 pretty fast, right?
Yeah.
But if I want to do XV plus V,
it's not intuitive.
Yeah, I mean, I'd have to know that this is 15 because I'm already cheating and using positional math in my head. And I would know that this is V. I mean, can you imagine doing a times table in ancient Rome?
Yes, okay. I've had to do math in Arabic, like Arabic numerals before. And it's just as intuitive as it is in our numeral system. The only thing that's difficult is that it's right to left.
Yes.
And so for the longest time, the switching is what gets me. So I would have like my Arabic back to back, and it would always just throw me a little bit because I would get so comfortable reading right to left and then switching to left to right. Like that was the hardest part, honestly, is not anything else. But
how are we going to do 2 times 2?
Oh, Lord.
I mean, 5 times 5?
25 is, what is that? Is that L?
It's no, XXV.
Okay. L is 50. I know that.
I don't want to do this. I mean, this is like torture. You know? This is like V times 3? V times I. Like, I can't believe I got this far. I mean, this is... Like, imagine learning this in school.
Poor Latin children.
Yeah,
we know why they conquered the world.
I mean, if they could understand this, they could conquer anything. Jesus. I mean, like, look at this. Sometimes it explodes into 3 digits. Sometimes it's 2 digits. You know, this one's bigger than, you know, this one. That one, even though this is only 2 digits, but that's 3 digits. I mean, this was a huge advance to stop doing this. Like, so yes, that's exactly the reason why we said, no, we don't want to put 15 as a symbol, because then what number is this? 115.
1 that doesn't, wait, I'm sorry. Are you saying it, are we, okay, so that's 115 in...
Well, no, that's decimal. I'm not writing this as I'm using your encoding. So let's say that we didn't use F, right? So this is like 1 and then that 15 pattern. Right?
Oh, so that's 45. Wait,
okay, you're translating back to decimal. You don't get to work in decimal. The computer doesn't get to work in decimal.
No. You said if I get my weird way of going 0 to 15. and booting over like base 15.
That's right. No, I'm saying I'm writing it your way. I'm not using the symbols A through F. So A through F are out. So I'm going to do...
Oh, okay. Yes, I got you.
I'm going to do hexadecimal, but I'm going to go 0, 1, 2, 3, da, da, da. And then I'm going to go
16.
10, 11, 12, 13, 14, 15. And then I'm going to roll over to 1, 0. And 1, 1. And da, 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 da. And then I'm going to get to like down here, and it's going to start looking kind of crazy. Like this is 1, 1, 0. And this is 1, 1, 1. And this is 1, 1, 2, right? And that was all fine, except how do I know when I look at this number that it's 1, 1, 2 with the 12 on the right and this thing on the left versus it's 1, 1, 2. and this was just a 2 in this digit and this was an 11. I mean, we're right back to this Roman mess.
1, 1, 0, 2. That's the same BS that's the same stuff that binary has been doing the entire time, though. Is that like, how do I know that 1, 0, 1, 1 is 10/11 and not 1/11 or 1, 0, 1/1? It's the same sort of like, I feel like
because every single, since there's only basically, since I know that all of the numbers that are in the base fit into a single position, I know that if I write this unambiguously, like if I know that I'm writing binary, then like I know that this is a 1 in the 2 to the 1 place. And I know this is a 1 in the 2 to the 0 place.
Yes.
And I know that this is a 1 in the 2 to the 2 place. Right? Because there's every symbol corresponds to only one one
7
digit. Right.
Yes.
So if I break that by doing this, now I suddenly have a parsing problem because like 115, I don't know if that's 1 and a 15 or if that's an 11 and a 5.
Yeah, I mean, I see what you're saying. I guess I'm being a tiny bit of a troll,
in just so far as like
so much of how we represent semantic meaning is convention, and so functionally speaking, there is no difference as to whether we have something that operates in the sense that written right there or operates in the way that we have hex. It's a matter of like convention and representation of meaning. But
Yes.
I'm really like that's I'm going like super troll there.
No,
and I'm not trying
that's
to
not
like
troll at all.
detract. It's just like
why are we doing this in the first place? Because we got tired of writing out all the things. I mean, I could just write out one triangle for every thing. So how many triangles is this?
9.
Yeah. I mean, that's nice that I put it in a nice square for you, but I can, I can kind of troll you back. And go,
okay, I got you. 12, 13. I'm following.
So like,
can't pull one from me.
Like this sucks to read, right? I mean, that was the whole reason we went with the encoding in the first place, because we didn't want to write this, right? We would much rather write this out as however many of these friggin' things I just drew, like, so this was my 9, 10, 11, 12, 13. So I would rather write this because this is a much more compact representation of all that. And that's exactly why we're going to do hex. We're doing hex because the computer's really working on binary, which is the truth. That's actually what's implemented in the hardware. So I can look at it with my electron microscope and I can see bits flying around. But we give them positional meaning by putting them into strings of bits, right? So that was like, if I have a 32-bit number, then it's going to be a lot of bits that I'm going to have to write out here. So this is my 16, and here's 32. Okay, this is not fun to write. So we want a more compact representation of that. And that's basically hex. We just say by convention, if we just break this into groups of 4, then one of these groups of 4, and I just got a straight line there, but one of these groups of 4 corresponds to a single hex digit.
Okay, yes.
So I can represent this 1111 as F, because that's actually what it is on the hex table. If I count it out, 1, 2, 3, da, 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 da. If I end up at F, that's all the bits lit up. So D would be like I did before, this would be that, and then I'm basically just going backwards in binary. Okay, so this is actually what the computer's doing. this is just for us. So really long aside later, when I come back to this coding window for the 18 viewers that are still hanging out.
Hey, we've got.
Wow, this actually multiplied.
Love the nitty gritty as much as I do.
The nitty gritty was more.
It brings
viewers than. This kind of all right. That's another tangent. So
you know what? That's literally when I go on one.
That's literally when what?
Literally, no one cares about this. I have more. Like, I guess people care about this, so I'm going to continue to rant. Like, this is good. This is the happy.
You know what? You sold me. I'm getting a flask.
Let's do it.
We're doing it. Okay, we're gonna rename the C coding session just an engineer and an astrophysicist and a glass of flask.
Well, so there is this amazing stream that some sort of like Twitter associates of mine have been doing all on like drunk science. And I'm not saying people actually need to get drunk. I can't science when I've been drinking, but like a whole lot. But I think there's something to be said about two people from like very different backgrounds learning about a topic with, some tasty beverages. It's fascinating because as you've been explaining things to me, as hard as I've been working to like, activate the tiny baby coding brain that I have, I keep jumping back to like, my linguistics background or something. And that's what's been tripping me up in some ways is kind of this like, for the super nerds in chat, like I love you. There's probably maybe one of you, like the origins of representation of meaning, right? So source, the signified and the sign, like we have a concept that we need to represent with some kind of symbol. And we're taking that one step further because we're like, we need a symbol and we are limited to yes and no or 0 and 1.
Yep.
And so how can we chain these things together to represent complex meaning? Yep. And that's a fascinating linguistics problem, but
that's exactly what we're going to be doing in C, actually.
See, maybe when you teach, when linguists want to learn to program, they C.
I mean, but I think they have to come at it from the background you had. I think that makes more sense if you've been in a language like Python and you sort of have a better sense of like what's going on and how to get things done. And then you want to go, now, how does that work?
Mm-hmm. I mean, that's true. So when I am not by any means not a scientist. I'm not even a programmer, really. I'm sort of like a what would you call it? Like a aficionado, I guess. It's somebody who loves it. But
I would call you a programmer because you've been you've been writing programs and you've been running them.
Thank you. I mean, that's very sweet. But like when people come to me and they want to learn how to code, often, especially if they want just kind of a basic understanding of something to do to stretch their mind and to kind of get their feet wet, I do point them in the direction of Python because yes, while it is hand-holdy, while there are some hand-wavy stuff going on, it's intuitive and it's readable.
It's
and
pseudocode.
Yes. And that's the thing, right? It's like even just with a couple of weeks of learning Python, you can look and it makes sense.
Well, until you see a comprehension.
Yeah. Until you get to like the land that I'm in right now where I download. What? I don't understand.
And but yes, Strophium, I completely agree.
That's the beauty of it though. Like it's learnable. And
I do agree. Well,
like it's accessible. Let's put it that way.
Okay. Waxing philosophic aside, because we're going to need more hours if we're going to get into that.
There are many hours.
There are many hours. No, they're countable.
We're what are we? Are we base 12 or?
We can do the math at base 12 if you want. But all right, before we do that, let me just wrap this up because I know you had a little bit of a time constraint. So let me just wrap this up by saying what we did in our really long tangent of getting to Roman numerals and realizing why positional numbers are great, which is totally a different thing. That is okay. That limiting factor is really up to you.
Yeah.
So
you're fine.
I felt bad. I was trying to be. I'm like, we're way over already.
This is the beauty of learning.
Okay, well, what we were doing before we got into the mess of negative numbers was we were realizing that we had, with a basic 8-bit, if we have 8 bits worth of position, so this is all we're going to have, then the maximum number we could fill out looks like 1, 1, 1, 1, 1, 1, 1, 1, right?
Mm-hmm. Yes.
And the shorthand way of figuring out what that is in decimal is just add 1 to it here, which is going to cause all of these to overflow, and they all do their thing, and then you'll end up with like 1, 0, 0, 0, 0, 0, 0, 0, 0. Okay, so this corresponds to 2 to the 8th, okay, because this would be the 2 to the 7th digit. You know, putting a 1 there is 2 to the 7th. And so this is 2 to the 8th. So if I do that minus 1, I end up with my maximum number is 255. Now I can shift that range over because I have this problem with negative numbers. And that gets into that a little bit messy. And for some convention reasons that I'm not fully explaining, and I apologize for some of the hand wave, we're realizing that a really good way to do this is called the 2's complement. And we can go into a lot more detail on that for you later. But basically the idea is that it's a complement. So for every number, I can take this maximum thing, this 2 to the 8th, and I can subtract whatever number I want. So let's just call it x for the moment. And that's going to give me the x complement. And complement, not in the complementary sense, like, oh,
yes,
you're such a great x. You know, hey, x, how are you? Very much approve. Not this kind of compliment. So we're talking about the complement as in this is the matching part of x. So the matching part is the other thing. That's neat. Except here I had to choose how many bits I had, right? So this 8 bits corresponds to the basic char type. And when I adopt the standard convention, the standard character is signed, which means that I really only have 127 of these, and then I have a negative 128 of these. I forget which side we added on, but I think that's it. And that's my signed character. If I make char unsigned,
you're limiting yourself to just 120.
Actually, I'm removing the limit because here I was going from, in a normal character that was signed, I was going from 127 down to minus 128. And because of this little messy problem with like positive, negative 0, I had to stick that extra thing somewhere. And so I stuck it over here. Okay, so what happens if I relax that constraint and I say you can't have any of these?
So then you get 255.
Exactly.
Or 56.
What if I put those over here?
55.
I get another bit that I can use. It's no longer a sign bit. This used to be the sign bit.
So why would you ever use a signed character then?
Why would I ever want a negative number?
I mean, no, but I just tried. To put character and negative number, and it doesn't
hello,
work.
Last Miles. There's your dude, Last Miles. Show there.
Hey, hi. It's about time. Jeez.
I'm sorry to interrupt your question. What were you saying?
No. So you were saying like you can choose signed, unsigned, and so
yes,
I just tried to put character and negative number, and it didn't work. It like barfed out a bunch of problems at me. And so why it
that
makes
looks like
sense.
I've got some Python buggery there,
but like why would you ever need
that's a nice one.
your response of why would you ever want a negative number?
Well, the first problem that we have here is
numbers go negative, characters don't.
Okay, put char actually doesn't accept negative numbers to begin with.
I mean, that makes sense, right? It makes no sense. Why
the reason
would,
that blew up on stream is actually due to how I implemented this tool. That actually what it tried to do was you went past the ASCII range, and by default, Python will throw that away because it doesn't know which encoding you're choosing. So it just defaults to crashing, which is kind of a sane thing to do, it turns out. But without answering that question, why would I want a negative character? I don't. Okay, it actually has to do more with the fact that I really don't want negative characters at all. What do I really want in terms of negative things?
Terms number?
Yeah. When am I going to want something to be negative? When we're dealing with numbers, not characters. Like, it's a little bit abstract to talk about character being positive or negative. It's just adopting all the conventions that regular numbers do. Now, I told you before how many bits was in an integer we're using the C99 standard. So in the C99 standard, how many bits were in an integer?
8.
No, see
I'm guessing.
that was char.
I don't know.
No,
I'm
that's
sorry.
okay. We didn't talk too much about it. This was actually the main meat of what we were going to get to earlier. Before
16. I'm just going to keep going up by.
Yeah. So it used to be 16 back in older standards. So it's not anymore.
I mean, I know. At least in Python, I usually deal. But I'm not sure which one.
Well, double this number, or double this 16, and you're going to get the right answer.
32.
Yes. By the time we got to the C99 standard, it was already standardized as 32. Int used to be defined as a convenient size for the architecture that you're on, which was very bad for writing portable code because everybody was, I mean, this had to do in an era when there were like 8-bit bytes and there were 12-bit bytes and there were, other weird things that you could do in hardware, and so that era is kind of gone. So we're talking more about like modern C, where int becomes a 32-bit thing pretty much all the time. But if we accept 32 bits, then what's the maximum number that I can have?
Whatever, 32 ones. So
exactly.
I'm not gonna. Yeah, I'm sorry. I'm not gonna do that.
So basically, I've got 4 groups of 8. Right? Mm-hmm. I could think of this as 8, 8, 8, 8. Right?
Right.
I mean, if I add these together, I get 32. Chat, check my math. That's...
I think so.
Stream lag here.
This is probably going to be. I feel like this go off like when I asked about negative characters, or signed characters. How the heck do you do floats?
Oh, we're gonna get to that in a moment. But
okay, all right.
Let's finish this.
My brain's hurting now.
No, I know, and it'll really hurt if I answer your question about floats.
Decimals, what? Because I could see you doing decimals as if somehow in Magic binary land, binary became not binary, and I was able to add a negative, then I could see like, or somehow we were able to kind of like go negative.
Yeah, when we're working with numbers,
right?
We do want things to be able to go negative, right?
Yes.
This has a lot more meaning than like a plus or minus integer has a lot more meaning than a plus or minus character, which this is a little bit silly, but that's
why I got stuck. So I was
this sort of fell out of the standard for reasons we're going to get to later, but you wanted to know C, right?
I'm here for the fun.
Okay, so this was this integer is kind of where it's more meaningful, and there we're still adopting the same convention, which is we need to keep 1 bit available for sign, and again we're going to use this 2 complement thing when we're going negative. So basically our algorithm is going to be like less than 0, then 2's complement.
Yep. Okay. Yep.
Okay, and greater than or equal to 0, just normal. So that's our way of dealing with sign, exactly the same as with char. Now I showed you with char because char is only 8, so I didn't have to write that much. If I was writing out 32 bits for every single line, we'd be in a lot of trouble. So that is basically why we also like to we stop using binary at this point. And we just split these. Each one of these 8s corresponds to 2 hex digits. So FF, F being 1111 from my earlier bit pattern. Mm-hmm. This corresponds.
These hexes are 4. Yep.
Yeah. So basically, if I put 2 of these hex digits together, I get 8 bits. So there you go. Not trick question. How many hex digits do I need to represent a 32-bit number? I mean, the biggest one I'll just write out for you.
So 8, right? Because each hex digit is 4.
Yep.
And so 32 divided by 4 is 8.
You got it. So this is really convenient that we get to hex by the time we're writing numbers that are this big. And that's exactly what showed up in the chat, by the way. So earlier they were like, okay, what is the biggest number that you could represent? It's this. It's 8 Fs. F, 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 F. So this would be the biggest 32-bit number you could have, as long as we're not treating it as signed, because otherwise this last digit here, this 1, corresponds to a negative number. So this would not be the biggest number you could have. if I'm using a signed integer type.
I'm sorry, light bulb moment. Okay. Well, nope. This is something probably, I'm so sorry, you probably an hour ago, but just sunk in is, wow, that's why you have to specify the difference between unsigned and signed. Is that
I'm answering your
unsigned gives you a bigger range, but if you need negative numbers, it's going to cut off like your positive.
That's
right.
Exactly it.
Oh my gosh. Okay, sorry. The light bulb, like, eureka, it happened. I'm sorry, you probably forever ago, but my brain just caught up and got it.
So. Totally fine. I was actually very long aside to answer your question.
All right. That feels good to actually get that. Like, okay, I understand.
That's where we needed to get to. And that's actually, now it's a lot more meaningful when I'm talking about integers having a sign as opposed to characters having a sign, because characters are just representing symbols in their base capacity, which is what the word character it refers to a symbol, like an A, a B, a C, that kind of thing. But and that all fit really nicely in 8 bits, because 8 bits, what was the maximum that I could have?
Oh Lord, 8 bits. Oh shoot.
It's 2 to the 8th.
Is that 255?
Yeah.
Is that 255?
Yeah. So it's actually 2 to the 8th minus 1, because, otherwise you overflow. So that's 255. So that means I get 255 symbols that I can assign, 255 different bit patterns, right? I can have 0, 0, 0, 0, 0, 0, 0, 0. I can have 0, 0, 0, 0, 0, 0, 0, 1, and so on. There's 255 of these. Okay, why is this convenient? Well, that's enough space to have all of the uppercase letters. Oh, there I go, writing in hex. All of the uppercase letters, which corresponds to 26, right?
Mm-hmm.
All of the lowercase letters, which corresponds to another 26. So I need at least 2 of these, right? I need 52.
Yep.
To be able to represent all of the uppercase and all of the lowercase. Old computers didn't used to do this, by the way. They didn't have lowercase, so everything was kind of uppercase back then. So you could save yourself a bunch of bits that way. But we like lowercase letters, right? I'm a fan. I don't know about you.
Yeah. Why not?
What other symbols do we have that we need to represent? Well, we have 0 to 9. They need symbols. And then we have stuff like a plus, a minus, an asterisk, a caret, a square bracket, another square bracket, a brace, another... we have all this other symbology. So when you pack all that together, they said, okay, we need at least 5 bits at a minimum. Okay, because 5 bits corresponds to what's the biggest number?
Lord, somewhere between 128 and 256.
It's a little less than that. 2 to the 5th is what? 32.
Oh, is that okay? No, so it's 7 is exponents. God.
Yep.
Okay.
No,
Yes,
that's okay.
I'm with you. I'm sorry.
No, it's got to get you back to this planet.
Yeah, I've been in like different land in my brain.
Totally fine. So we have 2 to the 5th minus 1. That's going to be 32 minus 1 is 31. So that means that I've got the biggest number I have is 31, but that gives me 32 separate symbols because I also get 0. That's enough to encode one of these. So if I have 26 letters in my alphabet, I've got 26 plus I've got, another 7 available for all of the other symbols. Well, that's possible, but it skips over a lot of stuff, right?
Mm-hmm.
Because we wanted to have lowercase letters too. So if we want to have lowercase letters, what do we need to do?
More bits?
Yeah, we need another bit. I mean, if we want to include that, we need at least 6 bits. Now, if we want to start adding like control characters, like, okay, take the printer that you're running and have it scroll up a line when I'm done printing this thing. So we have all these control characters as well. Well, what do we do with those? Well, all right, we'll call it 7 bits, okay? And this is basically ASCII. This is the American Standard Code for Information Interchange. And that's where they stopped. They said, all right, 7 bits is cool.
I've always wondered what ASCII meant. Like I'm frantically trying to find my... Oh my gosh.
Because
okay.
America.
America. Yeah.
America. Okay, well, that's why ASCII. But that was fine as long as my letters looked like things like... So in 7 bits, what's my maximum number?
7 bits is, that one is 127.
You got it. So my biggest number is 127, and that includes my 26 characters of uppercase, my 26 characters of lowercase, a whole pile of symbols, a whole bunch of control characters, all that other stuff. We used up this entire thing because we want to be able to have the underscore, and we want to be able to have the hyphen as well, which looks similar unless they're on the same line. So, and then we want to be able to have things like braces, and then close braces, and then parenthesis, and then a close parenthesis, and then a square bracket, and then a closed square bracket. Okay, so all of this stuff, they ended up choosing, like, they said, all right, this fits into 7-bit. It's totally occupied. What were the Americans forgetting when they did this?
Accents.
Well, there's other parts of the world, aren't there? So
yeah, like other alphabets or just accents.
And so the original answer was, well, we're not going to answer that. And so everybody and their brother took the last bit. They said, all right, well, we're going to call this 8 bits because this is a power of 2.
So American.
And
I'm sorry, that's so American to just be like, yeah, no.
This part we're going to reserve. We're going to call this ASCII down here. Okay. Well, what does that leave for this? Like, if you use this sign bit, which we already went to town and back on why it's not really a sign bit, but
it's negatives. It means negative letters.
This expands our range to 8 bits. If we're using 8 bits, then what's the maximum number we can have?
255?
Yes. It's 2 to the 8th minus 1, which is 255. Okay, so that gives us 255 symbols, including the 0 null terminator thing, which is... Anyway, it gives us 256 total symbols.
The null bit.
Yes.
I remember the null bit.
Yep. And so this part was specified, and then everybody fought over this other part. And we got a whole pile of encoding messes. Like, this was like one thing after another. There was like, you could have like the IBM code pages. So you could have code page 7, whatever. I forget all the old code pages, like code page. Oh, we want that back. We could have like code page 430, or we could have like shift gis. We could have, one of the standards for representing ideograms. We could have things like this. We could have big 5 encoding. We could have all sorts.
You've lost me, but I assume this means something.
We could have EBCDIC. Yeah, basically, this actually was fighting sort of at the same time that this was fighting. But we could have, like, ISO standards. We could have ISO 8859.
Yeah, see, Nathaniel's right there with you. Like,
1,
yep, 8859, yep.
7, where do you put the Hebrew characters? Where do you put the Arabic characters? What do you do when you get to Chinese? How many characters are there in the Chinese language?
Well... Okay, nope. Linguist hat off. That's a rhetorical question. Yep, we're good. I'm nodding.
They're still discovering characters.
Let me get on my freaking platform.
Okay, but literacy, basic literacy is defined in China as about 2,000 characters.
Yep.
How many bits are you going to need to store 2,000 characters?
That's the fascinating thing about Chinese and similar languages is that you, instead of a particular symbol being associated with a sound, you have a symbol associated with a meaning. And so instead of having the breadths of sounds that the human sort of mouth anatomy can make, which is actually quite extensive.
That's Korean you're talking about, right?
you have the breadth of human meaning instead, which is okay. Yeah, so I was drawing a parallel between you have languages like English that encode sound with the symbol. So, we see a K, for example, and unless there's an N before it, we know it's K. It's a hard kind of like C sound. I won't go too linguistically into like the anatomy of your mouth. But then you have languages like, ancient Egyptian hieroglyphics, or in this particular case, like you're talking, Korean. Korean, I believe, is actually more like English, which encodes sound with a symbol.
You're talking about modern Korean.
Modern Korean, yes. And Chinese kanji.
Classical Korean does not. It uses the kanji style.
Really?
Yep.
That's interesting.
Same story with Vietnamese, by the way. Vietnamese now uses an alphabet, but does not in other cases, like in ancient texts, for example. So
that's really interesting.
So what do you do with the cardinality? Because if 2,000's basic literacy and more advanced schooling is like 8 to 10,000 characters, all of these are about the same cardinality. Like when you're talking about all of that stuff that I just mentioned. So you're talking about like easily 100,000 characters we need to add on. So how do we encode this? Well, that's a lot of bits.
I mean, the answer so far, like, you know, me, little student here learning, has always been add more bits. I mean, that's been the answer so far, right? Is like more bits. Wow. We need letters in the first place. More bits.
Yes, that is the answer. It would be more bits. And actually, the funny thing is that eventually we decided to take all of the different codes that were being created in all of these different places. Like, you know, there's the Japanese information standard. There's the Chinese was creating the big standard. You know, there's all sorts of like different. There's like the HKSAR extension of that. You know, there's all sorts of stuff that's going on to get all of these languages. Eventually, we said we don't need all of these different encodings.
Okay.
We
Why
need
not?
The one encoding.
What?
To rule them all, and in the darkness bind them.
Yeah. Okay.
We need the unit encoding. We need the Unicode.
No.
So this we eventually do solve this problem. And by the way, in C, it is going to be a nightmare. But we will get to that a little bit later because this stuff can get really crazy. Like there's a whole lot of stuff. That encoding is a topic that it's definitely advanced in this stuff. And we
well, that's the funny thing is that's something that I run into a lot because not obviously as a baby, but working in Python, one of the difficulties has been as I kind of work for clients that are less, how shall we say, technically advanced. And they're like, here, take my data repository in the scariest of scare quotes. And it's really just a hodgepodge of like Word documents, PDFs, figure it out. Encoding becomes a problem because as you start to try to scrape data from all of these different formats, I get a lot of encoding errors. And so I've had to kind of learn some of this, like not very well in this now, frantically panic Googling right before I have to like submit some code. But it's important. And even though I think for a lot of people, they might think this is too nitty gritty, this is too kind of under the hood. If you try, even as somebody who doesn't want to understand the under the hood, if you try to kind of write code for clients that don't already have a wonderful, perfect database system or, you know, storage system, whatever, for their data, and it's perfectly, you know, organized and whatever, then you're going to run into this stuff very, very fast. So I feel like this is actually what sort of started me on this path of wanting to learn a lot more, is running into problems like this and trying to kind of dig deeper and be like, why are they, what even is UTF-30? What does UTF even mean?
Yeah.
What are all these different random errors that I'm getting, and what is encoding? What is happening?
Yep.
And I think if you teach yourself code, that stuff pops up and you're like, huh? What is this stuff?
Yes.
And so it makes sense, you know? So this is very fascinating.
That's actually why Python threw earlier when you said -10, when you did a put char on -10, the back end of this web server is running in Python. And it's actually it's up in GitHub.
That's right.
You can
it's not running in C. It's running in Python.
It's not running in C. I wanted to actually ship it reasonably soon, so it's right here in main. But and what it's doing is it's realizing when you did this -10 that the number was outside of the normal ASCII range. And as soon as you leave the normal ASCII range, which is the bottom 7 bits, so when I go to the 8th bit, which is going to correspond to what number? So what's the biggest number I could get with 7 bits?
7 bits. Okay, so 127.
That's correct. So what happens as soon as I show the character 128? Bitwise, what did I just do?
So you've I mean, are you just going to get like an error of some kind? Because it's not
basically, I mean, you know, C has no problem doing it. Python does, on the other hand. Python very much has an opinion. And Python goes, hey, you got to choose an encoding. Like, I'm going to default to UTF. If you don't say anything, I'm going to default to UTF-8. And that's not a valid UTF-8 sequence. So,
oh, Python.
And that's actually a pretty reasonable default for a modern language. But C, on the other hand, has no opinion about it. It'll just display those bits, and it's up to the terminal to sort of say, well, I happen to be in this encoding, so I'm going to turn it into this. That's when you start to see like all sorts of crazy stuff. Okay, so yeah, we're totally going to get into a language war here.
Oh no! Oh no! No language.
Yeah,
you need one of those like chat
oh no
aliases just to be like war, and it's like no unless it's JavaScript, which
no, they're already talking about HTML, so this is about to get really dirty.
I have no idea what that is. Okay.
Now, Nathaniel, I don't want to see that kind of language in here.
Oh, no.
No
gloves,
HTML. So that's a pretty crazy standard that Nathaniel's referencing. Okay, but anyway, that's actually what happened. So as soon as I did this minus thing, oh my God, he's just
oh no, what is that? Please DSSS.
No, I won't.
3 S's? Hold on. I'm googling this. DSSS.
No. Okay, so
document style, semantics, and specification. Is this just LaTeX but sad?
Don't look at it. Don't look at it. Okay,
style sheets.
When I went back to your program and I changed the number from 128 to 127, I was staying within 8 bits of data. Or sorry, 7 bits of data. So C and Python both agreed they had no problem. They just displayed it. Now the character is actually a backspace, I believe. I think it's delete. I'd have to look.
Huh.
This.
Okay. Sorry. Yep. So this is where I'm sorry. Like this is. I'm sure for especially everyone in chat who's miles ahead of where I am right now. It makes a lot of sense.
Yeah, it's a delete.
Where, of course, there needs to be some kind of representation for the various keys that I have on my keyboard, because so far I've taken this sort of linguistic approach of we need representations of meaning, but to have a delete seems like it should be more of a function than it should be a character, if that makes sense. Well, like it's an operation.
How do you type it on a keyboard?
I mean, wouldn't you just kind of drop the last thing you did? Like,
yeah, but
maybe that's
then the keyboard would have to know the state of the computer to know what the last thing was.
Well,
that'd be a very expensive keyboard.
So I guess, again, it's super ignorant. So, like, people can laugh, but, like, I guess I thought, like, when you hit a backspace or something, that was a trigger.
It's a trigger, but it depends on the encoding. So it's like in old style, a backspace is right here. It's, it generates an 8. So,
I mean, that's really cool for me because my hardware and my software knowledge, there are many miles between them. And so when I've built the electronics that I've built, it's been very simplistic, but it makes sense that you would have representations. Like if I were to create the hardware that is this keyboard that I have in front of me, it would make sense that I would then want on the sort of internal level for the various keys. So that does make sense, but I know for so many people right now it's duh, but for folks like me who are more like self-taught, that actually is fascinating. That's really interesting that it's not just
oversimplifying, because the keyboard actually generates a scan code. It doesn't do exactly what we're saying. It doesn't turn it necessarily into ASCII, but
okay.
I don't want to go too deep into that. But I mean, the moral of the story is that like even older hardware, like the terminals they're taught, like the VT100 that got brought up in chat, or the fact that originally this stuff was hooked up to a printer or punch cards or whatever. We needed a way to represent everything that was kind of going on. And yeah, I agree with you. I think that is fascinating. I mean, I had to learn it too at one point. I wouldn't call it duh. I'd call it like probably something you never thought about, especially in Python.
It's just, I guess this is again that kind of writing notes. Sorry. This is the interesting sort of connection that I want to make at some point, is that I've built, I would say, very primitive electronics myself on a hardware perspective. So like The most complicated thing I built is like a whack-a-mole machine.
Yep.
And it was really fun. I got to learn a lot about circuits, and I learned a lot very fast. I stayed up for 38 hours. It was a really bad time, but it was actually... I think that there's almost like not a sort of crotchety boomer, if you will, sorry friends, like taking it for granted kind of mentality, but there's just it's so easy now to learn Python, to say things like, to just hit a backspace, to print things very simply, very easily, especially in Jupyter Notebooks. And so, especially as you have started to teach me C, and I've realized that even just kind of printing things out is a lot harder than I expected. But also, like, how do we represent these things? How do we go from that higher level of on-off to the full complexity of what we need to encode? That's really cool, and it's not intuitive. It's not something that I've really thought about.
It's not.
So it's really, really cool.
No, it really, yes. I completely agree with that. I don't think I have anything to say to that. I think that was more of a you're thinking out loud. But
yeah, sorry. I don't.
No, that's all right. I
feel like
nothing I heard in there was wrong.
About computers tonight. I really do. I feel like I'm going to dream about this. I just have that feeling.
No,
this is
totally
really cool.
Okay, well, let's go just one. I just want to close this up with like one little bit because we've done very little C code. So you shall not pass.
Sorry, I'm sassing Strophium because yes, Balrog, so I was sassing.
Oh, wow. Yeah. Yeah.
I aim to be the computer science Gandalf.
Okay, awesome. Well, let's grow your beard
have
a
that,
little more.
I don't have that follicular power. I just don't. So I'm sorry. Okay, but yes, let us continue.
Okay. So here we are. We were putting cares. We learned a little bit more about how all that's organized. But let's get back to our basic types. So we had an int, right? So if I have like an integer A, we had a char, like I had a character B, and we also had float, which we didn't really talk too much about. Like I'm just jumping ahead with letters.
That's fine. That sounds scary in terms of going depth that we did. I will leave that for another
Q or something.
Yeah,
we're gonna get to that later. So these two basic types, I've been kind of hammering at how they're stored in memory, but C actually does give you an operator to figure that out as well, and it's called the size of operator, and it does pretty much what it says. So how do I print out a number? Just going back real quick.
Okay, so a number, we can
use the routine. Don't do it by hand.
And we would put some stuff with percentages. I think
except we have to mind our quotes because we're in C, not Python.
Oh, shoot, sorry. Okay, percent %D, and then I think there's like a /n maybe.
Yep. Except that's a front slash.
Okay, /1. Ugh. Okay,
there it is.
Windows.
Yep.
All right, and
that's
then
a new line. Then whatever the number is. Yeah, 3. That sounds good.
Yay! I did it. Okay.
Except we need a semicolon because we're in C.
Yes.
Okay, so let's get rid of the other put care. I'm just going to comment that out. Go ahead and run that program.
Okie dokie. Execute. Yeah! All right.
Let me clear the output. All right, so we execute that. We're able to put a number on console. Now, how big do you think that int is? That int A?
Hang on a second. Give me a second. Okay, I got this. It is 2 bits.
Okay. Our theory is it's 2 bits. You're calling that a 2-bit integer, huh?
I don't know. I'm trying. Okay.
That was my pun.
My
Sorry.
hour-long knowledge of binary. Yes,
no, it's totally fine. If I talked about the character, so why don't we have the computer tell us? Let's not guess.
Okay.
That's the size of operator. So why don't we say, what is the size of A?
Oh God, there's no parentheses. All right. Yep, we're good.
No, because it's not a function. It's an operator.
Oh. Okay, but all right. We're fine. Yes, I'm good. Okay.
Yeah, go ahead. So
what?
What? What?
Oh, wait. I got you. Hold on. So, hang on. I have a theory here. I'm going to use Python language. I'm sorry. I don't know the right language to use.
Don't form a theory yet. Don't form a theory yet. Hold that.
Oh,
Hold that theory from
I
forming.
think I know.
Hold that theory from forming. What happens if we look at this?
8.
It's 8.
What?
It's 8 bits.
What?
It's 8 bits. You're correct.
1 byte.
Which is 1 byte.
Yes. Okay. All right.
So what's that for?
4
bytes,
16 bits.
4 bytes is not 16. It's
wait. If one byte is
8
is 8 32.
Bits,
32. I'm sorry.
Exactly.
Oof. All right.
So
the caffeine has long worn off.
No, that's totally fine. We're definitely getting late. So that's why we're going to wrap up with this operator. Yeah, don't worry.
This is when my brain starts to play like.
No, we're good. In fact, we should have got there earlier, but we spent all those brain cells on encoding and bits and 2's complements and everything else. So, okay. We have a way of telling what the size is. The only catch is that it shows up in bytes. Sound good?
Okay. Yes.
Okay. So if I do the size of it, pretty much it works with types. So I can say, give me the size of a char.
Now I'm a little confused. I'm sorry. So this is where, again, this patchy knowledge of mine is probably going to become an obstacle, where I thought that okay. Oh Lord, this is probably going to be very ignorant, but I thought that the difference between bytes and bits was not kind of like an 8-to-1 whatever.
It is.
I thought it was one is a rate for like internet speeds, right? And one is more of like
that's how it
static
came to
memory.
You. No, we're talking about what it is at its core.
Okay, all right.
And by the way,
and I'm just clarifying so that like I'm sorry that like
you're not
that's
wrong.
How
but the
I
problem
sort
is that comes from a very different domain.
Okay.
And that kind of comes from the fact that bits themselves correspond to what is a bit? It's a binary digit.
Right.
I'm gonna
yep.
Take the pads that
I got you there. Like that makes sense.
Binary
bits
digit.
Bits are my happy place, and then we went to bytes.
Bit.
And okay. Yes.
It comes from the word binary digit. It's just a contraction. Okay. So digit being just decimal. If we don't specify, then this is usually base 10. So this is kind of like the numbers we're used to. Okay.
Yep.
What is a byte? Well, it's just a chunk of bits. Different standards historically got into a whole bunch of fights, but we're doing C99, so that means
Why wouldn't you just call it like a octo bit?
And actually, that's exactly how it's referred to in the standard. Standards refer to it as octets. Why do they use octets? Because it's unambiguous.
Thank you.
And back in the day when there were 12-bit bytes and 8-bit bytes and 4-bit bytes, and every different manufacturer chose a different number for what byte means. Well, octet was a story, right? And so the standards documents, whenever you look at them, they're going to refer to octets because this is always 8 bits. There was never a difference from this.
That makes more sense than a byte, to be honest. I'm sorry.
Well,
like
that's
we have scientification, wonderful standards.
I didn't invent the world.
I know. I'm just you are the representation of all of the knowledge.
You're gonna need to know bytes
so you can fix it.
In the modern world, you can treat a byte as an octet. You can treat these pretty much interchangeably. But if we do look at some libraries when we look at some C code later, we're gonna see that there's 12-bit bytes and all this other crap. So in the C99 standard, it's unambiguous. A byte is 8 bits. So we don't have to worry about that. It's always 8 bits as far as we're concerned. Okay, so if we know that, 32 bits shows up as how many bytes?
32 bits shows up as how many bytes? 4.
Correct, because 8 bits in a byte.
Yes.
All right, so size of operator returns bytes. You can guess what kind of fun there was in the standards at that point. So reasons, but no, we're not getting into Endianness.
People have been saying that already, and so all I know is
we talked about it briefly in the lecture earlier, but basically it's just kind of you're writing left to right or right to left when you're going across bytes. But bytes, as we learned, are already a little bit messy. But what I can tell you is that networking that we brought up briefly when you were talking about bits and bytes, computers kind of grew up using bytes as storage, so like we would say, like, how many bytes does your hard drive have? I mean,
right.
It's been a long time since we said that, but I mean, like, obviously byte was not a very convenient unit. So we started using kilobytes, and then we started using megabytes, and then we started using gigabytes, and then terabytes. And we can eventually go into the future in Star Trek, and we could start calling them quads, because F it. So
Star Trek. Oh yeah.
How many?
But I mean, that's
teraquads?
The kind of thing of, like,
I mean,
we should have just stayed with, I don't know. I mean,
well, I'm not going to get into. That's more of a history talk. But
you're fine.
What I am going to say is that this byte world grew up around computers. Now, networks, on the other hand, they were concerned with like Morse code kind of stuff. Like how many like dits and das did you pass, which would correspond to binary. So how many binary digits passed on this wire? And so they started using bits. I don't really know what the original reason was. I think it was to make themselves feel better about how slow their streams were, because when you get people to start talking about bits, suddenly things seem a lot faster, right? Because the numbers inflate by a factor of 8.
Fair enough. Okay. All right.
So they adopted the convention in networking of using bits. I mean, they're literally using wires connecting networks. I mean, so it's not too crazy that they would be operating on bits, especially when you talk about serial and some other stuff that we're not going to get into right now. But they adopted the convention of using bits. So yes, to your comment, like when people usually refer to like megabits, they're almost always referring to a network speed.
Speed, right? Yeah. Okay. So I always thought it was like, this is computer science people's way of distinguishing meters versus meters per second. They just use different words.
No, that's just they both refer to like if you're talking about megabits, it's actually megabits per second. So like Mbps was kind of referring to like megabits per second, because back in the day we had modems that were measured in bits per second. Like,
oh, I've been there.
Yeah.
It was sad.
And then eventually we had kilobits per second, and then eventually we had megabits per second. And if you're in a really good part of the country, you might get gigabits per second. And if you're over at Netflix's campus, you actually get a terabit, which is pretty cool.
Oh, what?
Which is just absurd. It's so absurdly fast that generally you're just waiting for the other server. I mean, it's kind of crazy. Something bad happened, which is why I'm not answering your question about SI units, and I don't want to get into that.
No worries, you're fine. You're fine. You can give me kind of like just old please, and as long as you come back to it at some point in the future, I'll be.
Yeah, that has to do more with storage manufacturers and then non-standards and lying and feeling good. But anyway, we're dealing in powers of 2 and we're dealing in bits, so we're not worried about that stuff. Okay, so now we know how to get the size of a particular variable, right?
Yes. Via size of the operator, not function.
That's correct. And it's sort of like in Python 2 when you had print.
Print was not Python 2 makes me sad. Nope. You had
print stuff, right?
I like the parentheses because it's like this little package. It's like math.
Well, because they eventually said, like, why is this not a function? I mean, this should not be an operator.
But that's the thing. I'm sorry, but like, look at math, right? Okay, I'm gonna. Sorry, it's math sass for. If I have x times y plus z, this means very different than.
Sure.
And so it makes a lot of sense that if I say, there is it doesn't matter if it's an operator or a function. It's an operator and I want, stuff. I'm going to put it in parentheses to give it its scope of operation. That makes so much sense. The size of thing bothers me a tiny little bit, but I will get over it.
Well, fortunately in C, there's very few operators. I mean, like size of and return. I mean, there's not many more.
I mean, that's fine. I literally just, the parentheses makes it similar to math. It makes it easier to parse, like my computer science programming order of operations.
Return is not a function, so we're not allowed to write this.
but okay, well.
Okay, so
I like it that way.
Yeah, I know.
Let's make our own programming language. No,
oh, hold on. We're gonna learn C first.
Yeah.
Don't open that can of worms quite yet. Okay, so that's, I think, probably a pretty good place for us to stop. I don't think we should go too far down. There's one little trick that I want to show you, which is, how did we do strings last time?
Strings. So I remember you telling me that print F is something that is from that include stdio.h. And so normally we wouldn't be able to print a string, but that kind of gives us that functionality. And so I remember being able to print strings using print F, but you mentioned that sort of in like the base C, if we don't import using Python language, import this particular functionality, we would only be able to kind of put char.
Yeah. I mean, that's it. That's all you get. Okay, so if we wanted to actually build that, that's fine. But back when I was building a string, we did a shorthand notation. And that got a little bit into memory representation, which I think we should probably just save this for next time. So when we wanted to do something like this,
it didn't work though, I thought, right?
Oh, it kind of works. Okay. I can make this legal if I play with it a little bit. But let's save this for let's save that for next time. I think we've done enough torture with math and representation. So all right. Well, I know chat has been very active.
This has been wonderful. I've learned so much. I know we kind of went off the lesson plan, and I appreciate that.
That doesn't bother me.
That's the wonderful thing about not learning this via some kind of college class, is that we can go down those rabbit holes, and that gives me that really deep background knowledge that I find is necessary when I want to build from a solid foundation.
Yeah.
Thank you. I appreciate it. I appreciate
we have to avoid some of the traps that chat keeps trying to get us into. Like, oh, hey, when are you going to do this? It's like, oh, okay, hold on. Let's build one thing at a time. Chat, I know you get excited with some of these new concepts, but I don't want to go too much too fast. Otherwise, we're just going to create a mess of Jess's mental model. So
I'm pretty resilient. Don't worry.
Well, then you're just going to look at it and go, wow, C's impossible. Forget it.
I'm very, very difficult to dissuade. That's don't worry.
Good. I'd rather dissuade you when we get to some memory stuff rather than give you too many operations at once. And then you're just like, I don't know. I don't remember all that. Okay, cool. Well, I think, I think that's a pretty good place to stop. Sorry, chat, if we didn't get too much into the topics. We did barely cover what we said with the review of types and size of struct. That's fine. I think
it's good to kind of, I don't know, it's nice to finally have those, not just be like, no, we're sticking to the lesson plan. Like, you're not teaching me to pass some test. Like, we're learning for the sake of learning.
We don't have a test.
That's the beauty, right? Like, that's the beauty, is like, we can learn whatever it is. Learn.
I mean, the only true test I'm going to see someday is like whether or not you could write a C program. Like,
someday,
if we go through all these like hours and you can't write any C, I'm going to feel that I failed you.
No, I've got that screenshot from my first for loop in C. I have that screenshot, and so you know what? We'll come back to it. We'll come back to it in like probably months, and we'll be like, yes, look at this progress.
Yeah, so. See, like look at Strophium in chat. I'm so stoked to teach you game dev now. It's like, okay, one step at a time. Before it's like, you know, going on about like, yeah, C is much easier to explain than C++. It's part of the reason we're starting there, but it also requires a bit more understanding of the architecture of the entire system, which is why we're getting a bit more into bits and bytes and fundamentals. Not Lord Byron, I thank you. I don't want to fend you all off too much. I mean, I want you to have fun too, but it's some of it. I think I'm worried for Jess's brain.
My brain is a hearty.
Yes, but
I don't think I've ever told you this. Like, I went into graduate astrophysics having not taken math in 7 years.
Oh,
I got
broke
you.
up a little bit at the end there. I missed the last
Oh
bit.
no, I just said that when I went into my graduate, I hadn't taken math since high school, so it had been 7 years.
Oh wow.
So I got you. My brain can handle it, and I will.
Oh, I'm not worried about whether your brain can handle it. I'm more worried about like if we're building enough cognitive scaffolding for you to, like I want you to acquire this knowledge. I don't want it to just sort of bounce off.
Nathaniel, so to answer your question, I did know calculus. I went to a really weird high school that taught all the way through multivariable calculus, but then I spent 4 years college, and I left early my senior year to study outside of high school, like I forget what they call it, like a dual enrollment. And so I hadn't had math in about 6 to 7 years by the time I entered graduate school. So
that's pretty cool.
Yeah. So I had it like 7 years previous, but it had been a while.
No, that's great, actually. I mean, I think you're doing well with it. Just, I do take more of the stance of Godfather that C++ does have a lot of stuff in it. Like, I think it's a lot easier to learn C first and then learn C++ if you want to go down that path, as opposed to learning C++ and then trying to make sense of C later. I think you'll end up... You gotta kind of get like a better model of the computer, I think, to really advance at C. But I
can't wait for that.
No, it's happening. I mean, this is already quite a bit. And thank you, Godfather, for the follow. I appreciate that. Learn all the things. Nice. I just saw your comment. All you need is GDB and some patience. That, not Lord Byron. That is probably the understatement of the century in terms of patience. But we'll get to GDB later. That's no test. What is this? Can't wait for that one. Yeah, I completely agree, Loafbun. I'm glad you all had fun. I'm glad that I wasn't having a drink. I think those rabbit holes would have been magnified. We would have shifted bits like crazy. But yeah, I don't. By the way, Strophium, I've seen that style of teaching. I really don't like it, where you talk about C++ without, like, you just sort of jump straight into the object-oriented aspects of it. But I feel like that doesn't really build a very good model. Like that teaches you how to work in C++ as quick as possible. But we're not in a race. We're not up against, like, she's not about to go into a corporate job for C++ like tomorrow. So I think if we were optimizing like time spent versus like payoff in corporate sector, then this is like, we're taking a longer curve to kind of build up to that knowledge. But I feel like you're gonna have a much better understanding of it, Jess, by the time we get there.
I honestly can't wait, and I like that approach. So I mean, I can do some OOP Python, but like, I constantly am aware of the fact that I'm missing that foundation, and I feel like these sessions where we're filling in those gaps, that really helps me feel like that foundation is growing. So
no, that's good. All right. Well, I mean, I'll be guided by you. I mean, I did put together like a curriculum, and I'm not a stickler for it. It's just more of like in an order of what I think you need in order to understand something else. Like otherwise we'll end up like wasting a lot of time. I'm just trying for better efficiency. Not that like there's anything in it that you're not going to understand. It's just like, why go too far down an advanced rabbit hole topic if you didn't build the fundamentals? Like, I'd rather we get to like pointers first before we start talking about handles, for example, or mmap.
Oh, well, we'll leave that. Oh, Lord. Yeah, we'll leave that for another day.
Oh man, we're getting into some serious Scotch discussion here, huh?
I know. I'm sorry. I love Scotch, and
you're
my,
killing me. That I'm gonna go.
My go-to drink. I'm sorry. Like, yes, I have my collection behind me. So I usually only drink Scotch video games because I can have a beer, and that's fine. But Scotch kind of hits my head a little too fast, so I can have a couple glasses of Scotch and still be extremely good at video games. I cannot have a couple of glasses of Scotch and still be writing decent code.
It's tough, especially if you're learning some new code too. I mean, it's one thing if like you're replaying stuff you're really familiar with, but like this I think a lot of this stuff is going to be new concept for you coming from Python. So like why impair the brain?
yeah, I need all the brain cells I can have.
Why not spend all the brain cells
and
like, then later on impair the brain and have more fun because you're not trying to learn something at the same time?
Exactly. And Theraflu has probably taken like.
Yeah, that's already.
So I'm proud of my.
I'm proud of you too. That's tough for first session back after COVID.
Ooh, yeah, man. Like COVID's nasty. People, please stay home, wear masks, be healthy.
Just listen to her.
Please.
She's
gross.
In my ears, so I'm visually pointing at my headphones. But
yes.
She's physically located. Actually, let's see. Is that south? I think south's that way. So you're that way.
Yes. That away. That is south away.
You're
Wait, bananas?
over there.
Ew. Ugh. Strophium. I'm so sorry. That sounds very sweet. I'm sorry. I'm one of those freak people on the planet that sweets. So anything that sounds sweet, no.
So I feel a little bad. I ended up missing last Miles. I saw he had a comment where he was upset that I was using care. Which... Oh well. If he was still here, I would talk to him about using the unsigned types and the modern standard types, but
we'll get there.
We're using kind of the classic types for now. So yeah, I mean, having assigned care as the default, that's like in modern days, that's a little bit crazy for reasons that we got into in a lot of detail.
Which makes sense now. I understand, which is great because a lot of times right now I'm serving for some very junior data scientists, and so I want to be able to kind of have that background. They ask me questions, I'm not constantly going like, I'll get back to you. So I like having that. It makes sense. So if somebody someday asks me unsigned versus signed cares, I'm like, I got you. I know now. I can explain it. Sit down. We'll have coffee. It's good.
Yeah.
I got it.
No, totally. I mean, I think it's better model wise to like come through, you know, because like if the first version of a type like you just saw here with I don't know if you saw that in the chat, but strophium was just mentioned. This is one of the modern types.
Yes, I've seen that. Yep.
This is like, I think this is a little scary to look at if you've never seen types before. Like compared to like this line, this int a, like this is a lot simpler to look at and sort of comprehend. So yeah, we had to get into a bit about int and all the other stuff, and it's kind of non-standard due to history, but this version, which is the modern standard, that is totally unambiguous, and so that's written nowadays, which is much more, actually it's much better to see in like a C program. But if you're looking at like older programs, you're going to see stuff that looks more like this. In fact, you used to have to create this like uint stuff, you know, these like I think it was GCC that first introduced these, but you know, you used to like define this stuff for doing things. We shouldn't be doing that. All right, we're done.
Okay, no, yes, no, we're not going down another rabbit hole.
We're not going down that. Fault line, come on. Python doesn't have types. You could just do whatever and it just works out.
Not always true. There are type errors.
No, I know. But it's funny because Python is incredibly forgiving. Like, if there's any interpretation that makes sense, Python will give it to you. C, on the other hand, is much more unforgiving. It's more like that either compiles or it doesn't. And if it doesn't compile, like, well, I guess that property exists for Python too. So that's a bad example. But yeah, I mean, the whole notion of duck typing, like, well, I mean, you're actually intuitively familiar with it because you've been programming in Python. But like when we actually start implementing that kind of thing, keep in mind like something like Python is written in C. Like it takes a lot of lines to add that functionality. I can tell you that much.
I bet. I mean, it's so flexible that it's almost too.
No, it's great. But anyway. No strophium. No, I'm not showing her C++.
No, I have to go to bed, friends. I have a very early, well, not very, one of them got canceled, but still, people want me to be on camera way too early in the mornings. I cannot go down rabbit holes of whatever duck typing is, C++ and things like that. So next time though, you should follow some coding guy, and Mondays, I believe, is our
Yeah.
Jess
learning.
tries to learn C nights. So
What's
come
this
back,
try?
hang out.
You're
Right?
totally
I'm
gonna
doing
know
my best
C.
here.
You're gonna know C. Don't worry.
Not using semicolons.
But
at
I
the
do
end of
appreciate
things.
that. Yeah, I mean, follow the Monday sessions are like this. The other days are other stuff. I don't want to talk too much about it, but basically, I'm building a version of Netflix that you can from scratch. So
that's so cool. I'm sorry. I'm like, oh, like I printed out every letter of the alphabet. You're like, I'm gonna build Netflix. Like that is so cool.
Hey, I'm doing it in Python. You could totally follow along with that.
Ooh, yes. Okay, actually, if it's in Python, I have a chain.
I've tried to make that as accessible as possible. I was sort of challenged. I'm just so you all know, I don't work at Netflix. I used to work at Netflix. I was there for about 6 years. And I was getting a whole bunch of questions, which actually started talking about bits and bytes and how the internet works and data speeds and the way transfers work and the way streaming video works. Because everyone's like watching streaming video and they're like, hey, how does that work? And I'm like, kind of like this. And I started explaining it. And they were all like, no, it works this other way. And I was like, no, it doesn't at all. Like that's kind of way off. And so like one challenge led to another. And then all of a sudden I was like, you know what? Why don't we just do a mini series on how streaming works, like at a really high level? And so I tried to make it as accessible as possible. So that meant JavaScript to me.
Oh.
So that seems to be like the most common language that I've seen live coded on Twitch. So, but because I couldn't go 100% JavaScript without lobotomizing myself, I did the server stuff in Python. So that's kind of the split. I did not do the "Are you still watching" feature. I do know Gobfather exactly who did do that feature, and I'm not giving away the name of that person. So, which
is a terrible shaming feature.
It's not a shaming feature. This didn't work at all the way we thought it was going to work. That I don't know how much I should say about that and how much is closely guarded secret. And actually, no, it's totally not, because it's now user configurable. I think I should say nothing.
So. Yeah, I think you can turn it off. But
yeah, you have control over post-play now.
I have to go. I'm so sorry.
No, totally fine.
If you want to go, like, keep telling people about Netflix, I don't want to hamper the stream.
Moral of the story: if you all want to come back, I'm doing CSG Flicks on Wednesday and Friday. Otherwise, come back on Monday, and we'll be doing it. We'll be doing C with Jess and Python earlier in the day. All right, so let's wrap up. Let's just call it a day there. So anyway, thank you everybody for the follows. Thanks for hanging out. Thanks for chatting. Thanks for all of these things. And Jess, thank you for keeping your mind open and trying to master this language.
Teaching.
It's very difficult. So I appreciate it all. And chat, have a good time. And like Jess says, stay safe, wash your hands, stay home, all that stuff.
Bye, chat.
We'll get through this. Yes, and bye everybody.